행사에 참여하신 참가자 여러분들과 내빈 여러분들께서는 방명록에 서명하신 뒤에 객석에 자리해 주시길 바랍니다.
아름다운 자연과 문화가 흐르는 도시.
네,
네, 안내 말씀드리겠습니다. 잠시 후 1시 30분부터 In Commemoration of APEC 2025 APCTP Forum and Symposium on Prospective Quantum Technology가 시작될 예정입니다. 행사에 참여하신 참가자 여러분들과 내빈 여러분들께서는 방명록에 서명을 하신 뒤에 객석에 자리해 주시기 바랍니다. 네, 잠시 후 In Commemoration of APEC 2025 APCTP Forum and Symposium on Perspective Quantum Technology 행사를 시작하겠습니다. 모두 자리에 착석해 주시면 감사하겠습니다. Soon we will be starting in commemoration of APEC 2025 APCTP Forum and Symposium on Perspective Quantum Technology. Please take your seat and wait till the event to begin. 네, 지금부터 In Commemoration of APEC 2025 APCTP Forum and Symposium on Perspective Quantum Technology를 시작하도록 하겠습니다. 참석해주신 모든 내빈분들 그리고 참가자 여러분들께 감사의 말씀드리며 오늘 이 자리가 양자과학기술의 미래를 함께 그려가는 뜻깊은 시간이 되길 바랍니다. 네, 우선적으로 본 행사에 참석해주신 내빈 여러분들과 참석자 여러분들께 재단법인 아시아 태평양 이론 물리센터의 사사키 미사오 소장님의 따뜻한 환영 인사가 있겠습니다. 모두 큰 박수로 맞이해 주시기 바랍니다.
Well, hello, good afternoon, everybody. I have prepared this opening remarks, and which is probably printed in the booklet. And unfortunately, I don't remember what I wrote. But anyway, I do hope this, this symposium and forum will bring us a lot of interesting sort of new ideas and prospects for the future, and especially for APCTP. And I do hope we have a very fruitful discussions and outcomes from this forum and a symposium. So thank you very much.
네, 다음으로는 아시아 태평양 물리학회 연합회 최형준 회장님의 환영사가 있겠습니다. 큰 박수로 맞이해 주시기 바랍니다.
Distinguished guests, colleagues and friends, I extend my warmest welcome to everyone joining this special forum and symposium, both in person and online. The Association of Asia Pacific Physical Society, AAPPS, is an association of 21 physical societies in the Asia Pacific region. And its aim is to promote the advancement of knowledge in physics in the Asia Pacific region. AAPPS has maintained very close and collaborative relationship with the Asia Pacific Center for Theoretical Physics, APCTP, for a very long time. And it's a great pleasure to co-organize this special event. This special forum and symposium held here at APCTP in Pohang, Korea, is in celebration of two remarkable occasions: the United Nations proclamation of this year, 2025, as the International Year of Quantum Science and Technology, and the upcoming APEC Summit in Gyeongju, Korea, which is just next door to Pohang. As all of you may know very well, this year is 100 years after the historic scientific milestone in 1925, the establishment of quantum mechanics with systematic and mathematical ground. Together with the theory of relativity, the theory of quantum mechanics laid the foundation for modern science and technology, and has since enabled the human society to achieve profound discoveries and technological breakthroughs. Very recently, quantum science technology entered a new era. The focus of development has extended from electronic and material technologies to quantum information devices. And the pace of development has been exceeding our boldest expectations. In this context, this special forum and symposium cannot be more timely. In this event, we will explore the current landscape and future directions of quantum science and technology. Especially in the forum, we'll focus on public engagements, educations, and international collaborations. I strongly expect that insights shared this event will contribute greatly to the future of quantum science and technology in the Asia-Pacific region, including outreach and policies. I'm also very confident that AAPPS and APCTP will continue the close partnership with each other in playing a vital role in promoting science and technology in the Asia-Pacific region. I express my sincere thanks and once again my warmest welcome to all participants. Thank you very much.
네, 다음으로는 포항 공과대학교 정규열 부총장님께서 김성근 총장님을 대신하여 참석하셨는데요. 환영사가 이어지겠습니다. 한 번 더 큰 박수 부탁드리겠습니다.
I'm Provost of POSTECH, Gyuyol Jung. On behalf of President of POSTECH, Sung-Keun Kim, I'm going to give you a welcome address. Basically, I'm welcoming you. Such a hot temperature. So the temperature is like 100 Fahrenheit. So 100 Fahrenheit means body temperature. So thermal equilibrium between the atmosphere and your body. President Sung-Keun Kim is a very handsome person, so I'm not able to substitute him. But so he prepared his warm address, so I'm going to read on behalf of him. So he prepared the welcome address in Korean. 여러분 안녕하십니까? 올해는 경주에서 APEC 정상회의가 열릴 뿐 아니라 유엔이 세계 양자과학 및 기술의 해로 지정한 해이기도 합니다. 이를 기념하여 2025년 APEC 기념 양자기술의 현재와 미래를 주제로 국제 포럼과 심포지엄을 함께 준비해 주신 아시아태평양 이론물리센터 그리고 아시아태평양 이론물리학연합회에 깊이 감사를 드립니다. 아울러 이 뜻깊은 자리에 함께 해주신 세계 각국의 석학과 전문가, 경상북도와 포항시를 비롯한 모든 내빈 여러분께 환영과 감사의 인사를 드립니다. 양자과학은 21세기 과학기술 혁신의 핵심 분야로 정보통신, 보안, 센서 기술, 신소재 개발 등에서 국가 경쟁력과 인류의 미래를 좌우할 잠재력을 지니고 있습니다. 이러한 최첨단 분야는 기초과학의 깊은 이해와 창의적 응용 능력을 겸비한 인재 없이는 발전할 수 없습니다. 포스텍은 세계를 선도하는 창의적 글로벌 리더 양성이라는 비전 아래 교육과 연구의 혁신을 통해 미래를 준비하고 있습니다. 특히 2024년 개원한 포스텍 융합대학원 양자정보과학 전공을 통해 박사급 인력 180명 양성을 목표로 하고 있으며 최근 물리학과 연구팀은 눈 양자 얽힘의 새로운 형태 구현이라는 핵심 기술을 세계 최초로 달성하였습니다. 또한 양자 정보 소자 인력 양성 연구센터를 중심으로 국내 연구의 수준을 높이고 차세대 우수 연구 인력을 길러냄으로써 양자 기술 시대 국가 기술 경쟁력 확보에 기여하고 있습니다. 이번 행사는 단순히 최신 연구 성과를 공유하는 자리가 아니라 차세대 인재들에게 과학적 영감을 불어넣고 국제 공동 연구, 교육, 대중화라는 세 가지 축을 통해 양자과학의 현재를 점검하고 미래를 설계하는 장이 될 것입니다. 또한 대중 강연을 통해 시민들이 양자과학을 보다 친근하게 접하고 포럼과 심포지엄에서 산학연이 함께하는 구체적이고 실질적인 협력 모델이 논의되기를 기대합니다. 끝으로 오늘 귀한 지식과 비전을 나누어 주신 모든 연사와 참석자 여러분께 깊이 감사드리며 이 자리를 통해 싹튼 아이디어와 협력의 씨앗이 교육 혁신과 과학 발전으로 이어지기를 기원합니다. 여러분 모두의 건강과 건승을 바랍니다. 감사합니다. 포항공과대학교 총장 김성근 대신 발표드렸습니다.
네, 재단법인 아시아 태평양 물리센터의 서사키 마사오 소장님, 아시아 태평양 물리학회 연합회 최영준 회장님, 그리고 포항공과대학교 정규열 부총장님의 환영사까지 모두 감사히 잘 들었습니다. 이어서 바쁘신 일정에도 불구하고 저희 본 행사에 참석해 주신 내빈 여러분들을 간단하게 소개해 드리도록 하겠습니다. 우선 경상북도청의 최혁준 메타벅스 AI 과학국장님 참석하셨습니다. 포항시청의 서재원 정무특보님 참석하셨습니다. 포항시청의 김정표 일자리경제국장님 참석하셨습니다. 포항산업과학연구원 유병옥 원장님도 참석하셨습니다. 막스플랑크 한국 포스텍 연구소 박재훈 소장님 참석하셨습니다. 그래핀스퀘어 홍병희 대표님 참석하셨습니다. 네, 다음은 본 행사를 기념하기 위해서 자리를 빛내주신 저희 내빈 여러분들의 축사 시간이 있을 텐데요. 자리에 참석하지 못한 이상희 경북포항시 남구 울릉군 국회의원님께서는 영상을 통해서 축사를 보내주셨습니다. 다 함께 시청해 보도록 하겠습니다.
네, 존경하는 국내외 과학기술인 여러분, 그리고 내외 기빈 여러분, 정말 반갑습니다. 포항시 남구 울릉군 국회의원 이상휘입니다. 오늘 APEC 2025 기념 미래 양자기술 전방 포럼 및 심포지엄의 개최를 진심으로 축하드립니다. 이번 행사는 2025 경주 APEC 정상회의와 유엔이 지정한 세계 양자과학 및 기술의 해를 기념하여 마련된 아주 뜻깊은 자리입니다. 양자기술은 21세기 과학기술 패러다임을 근본적으로 바꾸고 인류 사회 전반의 혁신을 결인할 핵심 분야입니다. 전 세계가 이를 단순히 학문적 연구 주체가 아닌 국가 경쟁력과 안보를 좌우하는 전략기술을 인식하며 치열하게 주도권 경쟁을 벌이고 있습니다. 이러한 흐름 속에서 오늘 이 자리는 포항과 경북이 미래를 준비하는 국제협력의 시작점이 될 것입니다. 국회는 양자과학기술의 안정적 발전과 산업화를 뒷받침하기 위해 제도적 기반과 법적 지원을 지속적으로 강화하며 선진 연구 환경 구축에 최선을 다하고 있습니다. 이번 포럼 및 심포지엄을 계기로 해서 여러 연구기관 및 기업 간 과학기술 네트워크의 활발한 실행 중심의 협력과 포항, 경상북도가 아시아 태평양 지역의 과학기술 허브로 자리매김하기를 정말 기대합니다. 저는 국회 과학기술정보통신 방송통신위원회 위원으로서 대한민국이 기초연구와 첨단 과학기술 분야에서 세계와 함께 성장하도록 적극 지원하겠습니다. 또한 지역의 과학기술 역량이 국제 무대와 연결되고 청소년과 차세대 인재들이 글로벌 무대에서 활약할 수 있도록 지속적으로 관심을 갖고 뒷받침하겠습니다. 끝으로 오늘 행사를 준비해 주신 아시아 태평양 이론물리센터와 모든 관계자 여러분의 노고에 깊이 감사드립니다. 참석하신 모든 분들의 건강과 건강을 기원합니다. 감사합니다.
네, 다음으로는 경상북도 이철우 도지사님을 대신하여 참석해 주신 최혁준 메타버스 AI 국장님을 앞으로 모시겠습니다. 네, 큰 박수 부탁드립니다.
저도 기억 못해서 다 적어왔습니다. 존경하는 내외 귀빈 여러분, 그리고 국내외 과학기술인 여러분, 안녕하십니까? 경상북도 메타 AI 과학국장 최혁준입니다. 2025년 APEC 정상회의 기념 미래 양자기술 전망 포럼 및 심포지엄의 개최를 진심으로 축하드립니다. 이번 행사를 성실껏 정성껏 준비해 주신 아태물리센터, 아시아 태평양 물리학회 연합회 관계자 여러분, 그리고 이 자리를 빛내주신 국내외 스카이 여러분들께 진심으로 감사드립니다. 2025년은 매우 뜻깊은 해입니다. 양자역학의 기틀이 마련된 지 100주년이 되는 해이자 APEC 정상회의가 경주에서 열리는 역사적인 해이기도 합니다. APEC의 설립 뿌리를 둔 아태이론물리센터가 경북에서 양자과학기술의 미래를 논의하는 자리를 마련한 것은 매우 시의적절하며 과학기술과 국제사회가 함께 나아갈 새로운 100년의 출발을 상징한다고 생각합니다. 경상북도는 양자과학기술을 미래 성장 동력으로 인식하고 추진 전략 마련에 이어 조례 제정과 인구 산업, 인재 양성 기반 조성을 위해 지속적으로 노력해 왔습니다. 특히 포스텍을 중심으로 한 연구기관과 기업, 그리고 아태이론물리센터와의 협력을 통해 양자대학원, R&D 과제, 글로벌 협력 등 다양한 분야에서 가시적인 성과를 창출하고 있습니다. 양자기술은 국가 경쟁력과 산업 패러다임을 혁신하는 전략기술로 에너지, 바이오, 보안, 우주과학 등 거의 모든 분야에서 그 파급력이 클 것으로 전망됩니다. 국제사회에서도 양자기술에 대한 관심과 투자가 급격히 높아지고 있으며 그 발전은 인류가 함께 해결해야 할 공동의 과제입니다. 오늘의 이 행사가 각국의 지식과 경험이 활발히 교류되고 공동 연구와 혁신을 촉진하는 실질적인 협력의 장이 되기를 기원합니다. 함께해 주신 여러분 모두의 건강과 행복을 기원합니다. 감사합니다.
네, 다음으로는 이강덕 포항시장님을 대신하여 서재원 정무특보님께서 환영의 말씀 전달해 주시겠습니다. 네, 큰 박수 부탁드리겠습니다.
네, 여러분 반갑습니다. 방금 소개받은 방시 정무특보 서재원입니다. 오늘 이 뜻깊은 자리에 이강덕 시장님께서 직접 오셔서 축하와 격려와 여러분들과 함께 자리를 함에 불구하고 시 일정상 바쁜 관계로 오늘 특보인 제가 이 자리에 참석을 하게 된 점 먼저 양해 말씀을 드리고, 특히 오늘 그 우리 미래 양자기술 전망 심포지엄과 포럼을 개최 준비를 해주신 우리 아태 핵물리학 이론 우리 마사 사사키 마시오 회장님을 비롯한 관계자 여러분에게 진심으로 감사를 드리고 또 이러한 심포지엄과 포럼에 세계적으로 유명하신 우리 석학과 관계자 여러분이 방방문을 진심으로 환영합니다. 우리 포항은 정말 눈에 보이는 게 R&D 분야에서 잘 갖춰진 도시로서 지금 성장하고 있습니다. 오늘 APEC과 또 우리 양자기술 원년회를 맞이해서 오늘 이러한 행사를 통해서 좀 더 발전적인 어떤 과제물들이 서로 정보를 통해서 서로 공유하면서 더 나은 인류의 큰 이화지할 수 있는 그러한 포럼이 되기를 기원드리면서 오늘 포럼하신 모든 분들이 생산적이고 원론적인 어떤 우리 국가 과학 기술 발전에 크게 기여하리라 믿는 그런 자리가 되기를 기원드리면서 우리 포럼하는 기간 동안에 모든 분들이 건강과 건강이 함께하기를 기원드리겠습니다. 다시 한번 방방문을 진심으로 환영합니다. 감사합니다.
네, 다음으로는 포항시장님께서 특별히 축전도 함께 전달해 주셨는데요. 제가 대신 전달 드리도록 하겠습니다. 2025 경주 APEC 정상회의 개최를 기념하며 환동의 중심 도시 포항에서 미래 양자기술 전망 포럼 및 심포지엄이 열리게 된 것을 진심으로 축하드립니다. 뜻깊은 행사를 준비하시느라 애써주신 아시아태평양 이론물리센터 사사키 마사오 소장님과 관계자분들께 깊은 감사의 말씀을 드리며 바쁘신 일정 속에서도 귀한 걸음으로 참석해 주신 각국의 석학과 전문가 여러분께도 따뜻한 환영과 감사의 인사를 전합니다. 양자역학의 탄생 100주년을 맞고 있는 지금 양자과학기술은 AI, 정보통신, 의료와 같이 다양한 분야에서 혁신을 이룰 핵심 기술이자 미래산업의 새로운 동력으로 주목받고 있습니다. 이번 포럼과 심포지엄이 이러한 양자기술의 비전을 공유하고 국가 간의 긴밀한 협력을 모색하는 소중한 시간이 되길 희망하며 이를 통해 대한민국의 과학기술 역량을 높이는 것은 물론 국제사회와의 연대를 한층 강화하는 계기로 이어지길 기대합니다. 포항시는 아시아태평양 과학기술의 허브 도시로서 지역 미래세대 인재들이 세계를 향해 꿈을 펼치고 도전할 수 있도록 기초과학연구 지원과 글로벌 네트워크 확장을 위한 일에 꾸준히 힘써 나가도록 하겠습니다. 다시 한번 포럼과 심포지엄의 성공적인 개최를 축하드리며 참석하신 모든 분들의 가정에 건강과 행복이 늘 가득하길 기원합니다. 포항시장 이강덕 드림. 네, 더불어 자리에 참석하지 못하신 대전 유성굴 국회의원 그리고 국회 과학기술정보방송통신위원회 위원이신 황정화 국회의원님, 김정재 경북 포항시 북부 국회의원님께서도 축전을 보내주셨는데요. 아쉽지만 시간 관계상 여기서 생략하도록 하겠습니다. 이어서 저희 단체 사진 촬영이 우선적으로 있을 예정입니다. 내빈분들께서는 앞쪽으로 자리 이동해 주시면 감사하겠습니다. 네, 앞쪽으로 나오시면 됩니다. 네, 바닥에 틈새가 있어서 불안정할 수 있으니 조심해서 이동하시기 바랍니다. 네, 모두 정면에 카메라를 한번 바라봐 주시면 되겠습니다.
파이팅 포즈 한번 부탁드리겠습니다. 하나, 둘, 셋. 파이팅! 네, 감사합니다.
네, 이것으로 사진 촬영은 모두 마치겠습니다. 네, 다음 세션을 위해서 자리에 착석해 주시면 감사하겠습니다. 네, 바로 다음 세션으로 이어나가도록 할 텐데요. 네, 저희 잠시 네트워킹의 시간을 갖기 위해서 2분 정도 시간을 둔 후에 55분부터 다음 세션을 시작하도록 하겠습니다. 네, 안내 말씀드리겠습니다. 저희 2시부터 진행되는 포럼을 위해서 5분간 휴식 시간을 갖도록 하겠습니다. 2시 정각부터 시작하는 포럼을 위해서 5분 후에 자리에 착석해 주시기 바라며 그 사이에는 개인적인 시간을 보내셔도 좋습니다. 정확히 5분 뒤인 2시부터 포럼을 시작하도록 하겠습니다. 네, 2분 뒤인 2시 정각에 저희 포럼이 시작될 예정입니다. 참석해 주신 내빈분들과 방문객분들은 2분 뒤에 자리에 착석해 주시기 바랍니다. 네, 다시 한번 안내 말씀드리겠습니다. 2분 뒤인 2시부터 포럼이 시작될 예정입니다. 방문해 주신 내빈분들과 참관객 여러분들께서는 자리에 착석해 주시기 바랍니다.
시간 막힙니다.
Good afternoon, everyone. We are now ready to officially commence the In Commemoration of APEC 2025 APCTP Forum and Symposium on Perspective Quantum Technology. It is my great pleasure to introduce you the Professor Hyungjun Choi, the President of Association of Asia Pacific Physical Society and also Professor of Physics at Yonsei University since 2005. Professor Choi will be guiding us through the whole forum. Please welcome him with a warm round of applause. 큰 박수 부탁드리겠습니다.
Hello, can you hear me?
Yeah, so I'll introduce you.
May I start?
Yeah, just 1 minute. So, yeah, today is the first speaker is Jian Wei Pan. Let me introduce him very, very briefly. He graduated from University of Science and Technology of China, and then he received his PhD from University of Vienna. He's one of the pioneers in the quantum science and technology. Now he's a professor at the University of Science and Technology of Korea. Yeah, thank you. Please. Yeah.
Okay. So thank you, dear colleague and friends. Good afternoon. First of all, I would like to thank the APCTP for the kind invitation, which gave me the opportunity to share my views and progresses on quantum information through an online presentation, especially at the significant moment marking the 100 years anniversary of the birth of quantum mechanics. Over the past century, quantum mechanics has become one of the pillars of modern science and has given birth to major modern technology which fundamentally change our lives. Over the past century, quantum mechanics significantly change our life. So, and with the deepening understanding of quantum mechanics, physicists have developed groundbreaking technology for coherent manipulation of quantum systems. This consequently leads to the emerging quantum information science, including quantum communication, which can ensure secure information transfer, and quantum computation can greatly enhance the computing power, and the quantum metrology can promise high precision and sensitivity in measurement. So, with the development of quantum information technology, it is foreseen to establish a large-scale quantum network or quantum internet to provide secure communication via quantum key distribution and to connect quantum computer via quantum teleportation and achieving ultra-high quantum resolution via content sensor, and so on. So to turn content network from a dream into reality, the quantum community has been striving for over 4 decades. Although proof of principle demonstration has been achieved, for example, QKD and quantum teleportation achieved on laboratory table with a few years after the theoretical scheme, and for quantum communication were proposed, and these experiments were conducted only over extremely short distance. As you can see from here, is about tenths of centimeter. So by 2005, several groups has demonstrated QKD over 100 kilometer fiber. However, it was formed, and due to the imperfection of realistic quantum device, mainly due to imperfect single photon source and imperfect single photon detector, there are serious circular loophole in private parameters, making the secure distance of QKD and fiber was limited to the order of 10 kilometers. Therefore, there are two major challenges toward the large-scale secure quantum communication before we can promote any practical application. And first, we need to overcome the secure loophole caused by imperfection of realistic device. Second, we need to overcome the photon loss and in fiber to extend the distance of quantum communication. For example, in 1,000 kilometer telecom fiber, even with the perfect 10 gigahertz single photon source and ideal single photon detector, only 0.3 photon can be transmitted on average per century. So to solve the secure loophole caused by non-ideal single photon source, the coordinated QKD protocol was proposed in 2005 by Horn and Hao-Kwan Lo, and actually here is also there's some contribution from Korea scientist Huang. So in 2007, two independent teams, including us, implement the decoy state QKD over 100 kilometer fiber. So by 2013, following the scheme by Hao-Kwan Lo, we demonstrate the measurement by independent QKD, which is immune to any attack on detection. So thanks to ultra-precise frequency transfer technology, and recently, the distance of MDI QKD has reached more than 5 kilometer fiber in field fiber, and more than 1,000 kilometer in coiled fiber. So therefore, and according to Charles Burnett, in MDI QKD, and the EVIS untrusted device remains outside of Alice's and Bob trust enclosure, they need only trust themselves not to have inadvertently create a side channel to Eve through incompetent design of their DIY light source. In this way, and so with MDI QKD and controllable DIY light source, information theoretically QKD with realistic device can be approached properly. So how to extend the communication distance? So one possible solution for large-scale quantum communication is quantum repeater. So the central idea is to solve the problem of photon loss via entanglement swapping, and to solve the problem of decoherence via entanglement purification. And where entanglement purification and is a way to distill a subset of high intense state from a large set of less intense state. So experimentally, it imposes three major requirements: intense swapping and purification, and with high precision, and also quantum memory with high performance. So the first intense swapping experiment was done in 1998, and a few years later, we also implement a high precision fault tolerant intense swapping on a high precision 4-photon interferometer, and also via an visible purification protocol using lean optics in 2003, and we managed to experimentally demonstrate high precision entanglement purification. So the reason why we need quantum memory is because without quantum memory, the cost of the total results in multi-stage experiments of quantum repeater is proportional to 1 over to the p to the power of 2m, where p is the probability of emitting an entangled photon pair in each experimental run. Thus, the scheme is not scalable. However, if we know when the photon pair is created and can store them on demand, then the total cost to implement entangled purification and entangled swapping is proportional to 1 over p to the power of square. So in this way, we can thus achieve efficient entangled distribution between distant locations and realize scalable quantum network. So in 2001, and the DLCZ single photon repeater scheme was proposed. Yeah. So in this scheme, ultra high phase stability on the order of sub-nanometer sub-wavelength after propagation distance of a few hundred kilometers is required, which at that time is very difficult to achieve experimentally. So therefore, and in 2008, in 2007, we proposed a robust 2-photon quantum repeater scheme, which only requires stability on the order of a few hundred nanometer. So in 2008, we experimentally realized our scheme, and by making use of 2 laser cooled atomic ensemble over 300-meter fiber. So in order to enable long-distance quantum repeater, the storage time must be long enough to ensure every node and create entangled pair in a deterministic way, while the storage quantum state must be and convert back into photonic excitation with sufficient high efficiency to establish remote entanglement. Yeah. So in our experiments, 2008, the lifetime is only about 1 microsecond, and the retrieve and efficiency is only 35%. And from this figure, and you can see the lifetime has to be improved by 8 order of magnitude in order to fulfill the requirement of long-distance quantum repeater. So since then, many technological experimental efforts have been carried out, including employing clock state, which is insensitive to magnetic field, using a ring cavity to increase the retrieve efficiency, and using a 3-dimensional optic trap to confine the position of each atom so that we can suppress the atomic collision-induced decoherence. So after all these efforts, by 2016, and we managed to prolong the lifetime and prolong 1 microsecond to a sub-second, while still with high retrieval efficiency about 80%. So all these elements, in principle, the new result already allow us to use for realization of quantum repeater, enabling quantum communication at a distance of 500 kilometers. So to connect quantum memory node and with the fiber, and we also need to shift the atomic wavelength to the telecom wavelength. So with the developed frequency conversion technology, and we successfully achieve quantum entanglement between remote quantum memory over tens of kilometers in 2020. And moreover, based on this, we also managed to achieve the first multi-node entanglement-based quantum network over metropolitan areas. So very recently, the entanglement distance between quantum memory has been extended to 420 kilometers, and divide-independent QKD using entangled photon separated by 100-kilometer fiber was also demonstrated. However, and a practical quantum repeater over 1,000-kilometer scale might still need 10 more years. And so therefore, more than 24 years ago, and we already started to consider another polymeter solution for global scale QKD, using satellite in space. Since the satellite to the ground connection channel has significantly reduced photon loss, and especially for the reason the effective thickness of the atmosphere is only about 10 kilometers. So most of the photon propagation and is in empty space with very small absorption and turbulence. So since 2003, we have spent more than a decade in performing systematic ground tests for satellite-based quantum communication. So in 2004, and we did the first and ground test on distribution of entangled photon pair over 13 kilometers in Hefei city. For the first time, well beyond the effective thickness of the atmosphere. So few years and later, in 2011, we demonstrate both entanglement, entanglement distribution, and quantum teleportation in Qinghai Lake over 100-kilometer free space, and which verify the visibility of quantum communication and via high loss satellite to ground quantum channel. So in 2012, and we performed a full-scale verification of a satellite ground QKD under various simulated conditions of rapid motion and vibration, random movement of the satellite, and the turbulence and high channel loss, and overcoming all demand conditions for ground to satellite quantum heat distribution. So with all this development, after almost 14 years effort, in August 2016, and the first quantum satellite mission was successfully launched. So with the missile satellite, we achieved and the QKD between the satellite and the ground station at 1,000-kilometer scale. In this experiment, and the observed final key rate is about 100,000 bits per second, which is more than 20 order of magnitude higher than using telecom fiber. And we also achieve entanglement distribution and between two ground stations, which are separated for more than 1,200 kilometers. And moreover, we also achieve and we also achieve satellite to and ground to satellite quantum teleportation over 1,600 kilometers. And later, with missile satellite as a trusted relay, intercontinental QKD between Beijing and Vienna over distance of 7,600 kilometers has also been realized. So we successfully implement QKD and between ground station and in Beijing and Vienna. Okay, so for the time being and through international cooperation, we hope to jointly explore the visibility of global quantum communication. So, interestingly, and along with quantum communication, many technology of coherently manipulating photon has been developed, such as interference of independent photon, high precision quantum interference of independent photon, and phase variation, and single photon detection, and precise frequency and time dissemination. All this together and could also enable optical quantum information processing, including optical quantum computation. So, by manipulating photons, we have demonstrated a number of small-scale quantum computation algorithms. But all these demonstrations remain largely toys with very small size. So one may ask how to build a quantum computer which can really beat a classic computer. So given the huge technical challenge, as John Preskill proposed it, and our community set three-stage goal towards the ultimate realization of a practical quantum computer. So the first one is called it quantum computation advantage, which means the speed up is so overwhelmingly huge, such that no classic computer can perform the same task within a reasonable amount of time, and is unlikely overturning by any improvement of classical algorithm and hardware improvement. So the second one is to construct a quantum simulator to efficiently mimic the evolution of a complex system, such as the study of the mechanism of high TC superconducting and so on. And at the same time, we also need to develop quantum error correction technology and to overcome the inevitable qubit error and achieve large-scale manipulation of qubit. So third and the final goal is to realize universal and programmable quantum computation with the help of quantum error correction. So quantum computation advantage is an important milestone in quantum computation, by which one can show the essential difference between classical and quantum and physics. Just like using the Bell theorem and to refute Einstein's local reason, and establishing quantum computation advantage by using entanglement as a valuable resource would refute the extended church Turing thesis, which states a classic computer can simulate computational power of any physics process with polynomial overhead. So in 2019, and Google first announced quantum computation advantage with a 53 superconducting qubit quantum processor Sycamore generate a millions noise sample in 200 seconds, while a classic computer at that time, according to the known algorithm, would need 10,000 years. However, our recent study show that with the latest tensor network algorithm, the same task can be complete by a classic computer in about 14 seconds. So the advantage announced in 2019 has been overturned. So, and in the superconducting quantum computation, and in China, 18 months later, and we realized a 66-qubit superconducting processor, 主冲之, number 2, and realized strong quantum computing advantage via random circular sampling. So in 2024, Google's updated Sycamore to 73 qubit. The advantage ratio is enlarged to 9 order of magnitude compared to the achieved classical algorithm. So a few months later, the Chinese 105 qubit 主冲之 number 3 and is estimated to have advantage ratio up to 15 order of magnitude. So beside our effort in superconducting system and in the parallel development in 2020, and using photons, and we realized Gaussian boson sampling machine, 9张, showing strong computation advantage. In the first experiment, 9张 detect up to 76 photons, and its sampling rate is about 10 to the order of 5 times faster than classic computer with the currently known optimal algorithm. So most recently, the detect photon count already exceed 3,000, and with advantage ratio, up to 41 order of magnitude. So, however, and although we have quite some encouraging experimental progress in the field of quantum computation advantage, universal fault-tolerant quantum computer and is still far away. So fortunately, quantum simulation may already lead to important application in the near term. So recently, and we explored a bottom-up approach to observe the first fractional quantum Hall state using interacting photon. So our method is that we design and fabricate a new superconducting and resonate, call it plasmonium, such that only one photon can be confined in the resonate, but we will block the second photon to jump in. This is very much analog to the Coulomb and repulsion. And next, to mimic the effective of a strong magnetic field, which is traditionally and required by fractional quantum Hall effects, and we use precise controlled AC microwave to couple adjacent box. These create an artificial gauge field. So photon hopping through these lattices will accumulate barrel phase, much like the motion of a charged particle in the magnetic field. So we can then arrange this photon box into a 4x4 and lattices. So the entire system is highly controllable with the ability to adjust individually and program the photon interaction, providing a new avenue for experimental observation and manipulation. Then in the experiment, and we further prepare the target fractional quantum Hall state. And this was achieved through a process called adiabatic preparation, where we carefully involve the system from a simple and initial state of localized photon into the more complex correlated FQH state by gradually increase the coupling and strength and tuning all sides to resonance. Once prepared, we can characterize its property. So in the experiments, and we observe and the hallmark shallow flow of this photonic state, they move in a specific direction along the edge, and we even see inverse current pattern in the bulk of the system. So reduced current are appreciably suppressed. And next, we plot the two defining characteristic of fractional quantum Hall state. The first is the incompressibility. Imagine trying to squeeze a liquid, it resists. Similarly, our FQH photon state resistance changes in its density when apply small local potential. Then, and the second, and perhaps the most conclusive test is measuring the Hall conductivity. We found that the Hall conductivity is quantized at a value very close to 1/2, precisely what expected from this particular fractional quantum Hall state. So compared to other quantum systems, hard-code atoms have several specific advantages for quantum simulation. Since the interaction of atoms can be precisely controlled, thus various Hamiltonian can be implemented artificially. So one of the approximation application of optics and of optical lattices with hard-code atom is to achieve quantum simulation of Fermi-Hubbard model. So in the experiment, and we prepare a homogeneous Fermi gas with larger Fermi energy, and with the Bragg spectroscopy with lower transfer and moment, we observe the second zone attenuation and reveal the critical divergence of thermal conductivity. And furthermore, and we have developed a momentum resolved and endoscopy and observe pairing pseudo gap and landing support for the law of the performed pairing as a precursor of superfluidity. On this basis, and we further loading and the Fermi gas into a 3D and flat top optical lattice, and thus realize a 3D homogeneous fermionic Hubbard model with approximately 800,000 atoms. So we observe the critical divergence of the spin structure and effect, providing conclusive evidence of anti-ferromagnetic phase transition. And we're also working on quantum simulation of gauge potential with a neutral atom and the quantum simulation of hard-code chemistry with a molecule. So in the near future, and we plan to achieve manipulation of more than 10,000 atoms to study scalable multi-part entanglement and error correction, and to mimicking strongly correlated topological matter phase diagram and dynamics of hard-code chemistry. Okay, so to achieve a universal fault-tolerant quantum computer, quantum error correction is needed. However, the threshold of the tolerable error rate for the traditional quantum error correction code is remarkably low, which is about 10 to minus 5. This is extremely hard to achieve experimentally. So a possible solution is to explore the so-called topological quantum error correction, by which one can significantly relax the error threshold from 10 to minus 5 to 10 to minus 2. So, I mean, for the time being, the so-called surface code is the leading approach to topological quantum error correction, which has an advantage such as very high error threshold, which is about 1%, and also simple structure and well suited for planar architecture, and exponential suppression of logic error rate within the code distance. So with the state-of-the-art technical level, a surface code with about 100 physical qubits with a distance of d equal to 23 can already meet the requirement for fault-tolerant for fault-tolerant quantum computation. So here I would like to briefly mention and several of our recent progress. So I mean, several leading quantum computing groups are currently engaged in the experimental realization of surface code. In 2022, and two independent groups, including us, demonstrate the first repeatable error correction on d equal to 3 surface code. 1 year later, and Google's and Sycamore processor has implemented surface code with a code distance up to d equal to 5, demonstrating that the logic error and rate and decrease as the code distance increases. In the end of 2004, Google's Willow processor showed exponential logic error suppression with a distance from d equal to 3, 5 to d equal to 7. Most recently, based on our Zhu Chongzhi number 3 processor, we demonstrate d equal to 5 show exponentially logic error suppression of 1.444 and factor, which is 43% higher than the Google d equal to 5 result, and the surface code with d equal to 7, 9, 11 is in progress in our laboratory. So before and conclude my presentation, I would like to mention some future prospects. So in future, it is foreseen to establish a global quantum communication network and quantum network by combining metropolitan quantum communication network and intercity quantum communication connected by quantum repeater and long-distance quantum communication with quantum satellite. So the 5-bit quantum network is currently already mature and practical for quantum repeater. In about 10 years, it is expected to support quantum communication at a distance over 1,000 kilometers. As to satellite-based quantum communication, there are still several technology challenges need to be overcome. For example, as a lower satellite, and a single LEO satellite cannot cover the whole Earth directly. So the solution is to form a quantum constellation with a multi-low orbit satellite to build a more efficient network, and a GEO satellite with much longer mooring time to distribute many more keys than LEO satellite. To do so, a pre-requirement is to ensure the satellite can work in solar and radiation background. So, and actually 80 years ago, we have realized free space QKD in daylight, confirming the visibility of quantum constellation. And moreover, to implement a practical quantum constellation, we need a lower cost microsatellite, such a lightweight payload is needed. So recently, we have realized small size QKD payload, which is only about 20 kilogram. And so the first microsatellite for quantum communication was launched in July 2022. And we also developed a portable ground station with a weight less than 100 kilogram, with which and mobile quantum key distribution can be realized. So very recently, and we realized QKD and between and microsatellite and the portable ground station verifies the visibility of mobile quantum key distribution. Meanwhile, the first and GEO quantum satellite is currently under development, which is scheduled to be launched around the end of 2027. So actually, the large quantum communication network also provide a new platform for the study of quantum metrology. So with the GEO satellite, we also plan to implement entangled distribution over the scale of 10,000 kilometers. And with the help of global entangled distribution, one can entangle multi-atom in remote atomic clock and dramatically improve the short-term instability of the atomic clock. And on the other hand, and with the help of the ultra-precision optic atomic clock developed by our colleague and the optic frequency transfer technology and so on, we can achieve precise time and frequency dissemination with a long-term instability, which could be 4 orders of magnitude better than the conventional microwave-based method. So our GEO satellite will also carry optical clock with a fractional instability up to 10 to minus 19, enabling optical clock compression between China and Europe and South Africa. This will demonstrate the visibility of global precise time information sharing and lay the groundwork for a redefinition of the SI unit second. Recently, we have completed some preliminary tests, including optical clock with both stability and uncertainty below 5 times 10 to minus 18, and also free space dissemination of frequency with 10 to minus 19 instability over 100 kilometers. And with the help of long-distance quantum teleportation, one actually can also establish the so-called quantum-enhanced telescope area to achieve interference without directly transmitting satellite. Thus, the length of the baseline can be greatly increased. For this goal, we are currently constructing a quantum-enhanced telescope area with and baseline and on the order of kilometer. So moreover, in outer space, since the magnetic and gravitational noise are negligible, so fractional instability of the optical clock may even reach 10 to minus 20, minus 21. So with ultra-precise time information sharing network and long baseline interferometer, in future, we hope it will be possible to provide a new probe for fundamental physics, such as detecting lower and midband gravitational wave. Finally, I would like to mention our expectation. So in the field of quantum computation and simulation, our next 5-year plan, so by 2030, is to rely on the coherent manipulation of a few hundred or 2,000 qubits to realize quantum simulation, by which one can study the mechanism of high TC and corner Hall effect and so on. So in the next 10 to 15 years, it might be possible to extend up to millions of qubits to lay the foundation for universal quantum computation with the help of quantum error correction. So thank you for your attention.
Thank you very much. Because of time limit, we'll have received one question, if any. If not, yeah. Thank you very much.
I'm sorry, I cannot really hear you. Yeah.
Yeah. So I checked whether there's a question from the audience, but there's no question. So okay. So one question. Yeah, please.
Sorry, I really cannot hear your question for some reason. I don't know.
Yeah. So there will be a question now. Yeah.
Thank you for wonderful talks. And
So
actually,
for
I'm not the
clarification.
physicist. I'm a teacher for the science secondary school students. So I'm wondering how promising the quantum science technology for the not only for the college student, but for the secondary or the primary school student.
Excuse me.
Yeah.
So maybe, so the voice and the problem, I cannot hear your question.
Oh, yeah.
So I can only hear ooh, but I cannot hear your question.
Sorry. I want to know how promising.
So what is possible, and some colleague can just stand in front of the computer, maybe, I don't know.
Yeah. We have a connection problem. So do you hear me?
Very sorry.
And then no. Oh, okay. So we'll finish. We finished the first talk. Yeah. Thank you very much. And there.
Okay. If you have problem, just send me by email. Okay. Thank you. I'm sorry for the better connection.
Thank
All
you very
right.
much.
Bye bye. Thank you.
Bye bye. Yeah, so we'll continue to the forum, and we have 6 speakers. The first speaker is Professor Joseon Jai from Tokyo University of Science. Please. Yeah, this one. And this is the notebook is over there.
Over there. So I click this. Well, let's see. Oh, it's here. Okay. Well, thank you very much for the invitation, and I'm very happy to be here. I'm asked to speak about something that I don't usually do. I'm a physicist, but I was asked to talk about pointer. There's no pointer. International collaboration. There's a pointer someplace. No.
Over there and
Well, no. I mean laser pointer.
laser pointer here.
No. Yeah, okay, fine. Maybe I don't need it. And
Center.
yeah, all right, I'll speak it here. And so my title is Liberalism and Protectionism in International Collaboration in Quantum Science and Technology. It's a bit long. And here. So in science and technologies, it's something related things, but it's actually very different. Science is curiosity-driven knowledge and to understand the world. And technology, of course, it's a need-driven things. And they are tied very closely. Technology and science it's tied very strongly at this age. So as you can see, technology exists long before science, but after the birth of modern science, the technology and science is very tightly bound. And so what about international collaboration? So open sharing and collaboration are vital for progress of science and technology. So I have this 4-quarter of things. And then, so at the horizontal axis, you have liberalism and protectionism, and then it's a basic knowledge and applied knowledge. And okay, I have put players. You have a scientist, engineer, startup, government, and established industries scattered. And so as a scientist, science is the crown jewel of mankind and should be shared with everyone immediately. So we publish things very fast. So we are in this side, liberal and basic knowledge. And in the other side, the government thinks science and technology are vital for national security and economical growth. So they try to protect science and technology. And engineer, they said, technology need to be guarded by patent. They write patents, and then you can share. And established industry, they try to protect their technology and just make money, maximizing the profit. They don't want to share their knowledge, usually. And startup, they don't have enough technology, so they want to share as much as possible to increase their knowledge. So to do this international collaboration, I guess the best chance is to do it in this people with liberal mind, like scientists, engineer, and startups. Government and established industries harder to deal with. This is quite obvious. And so how do you do it? International research collaboration, it's to enhance knowledge transfer of the humankind. Knowledge always flow from high to low. This is like entropy. And so how do you do it? The easiest way I know, I have been doing this for more than, 40 years. We exchange, international exchange of the researcher or students. This is the easiest. And you can bring back your knowledge to your place and you exchange your knowledge. Or you exchange samples, and or you can ask someone to fabricate your samples. This is quite easily arranged. So I would say this is the easiest way to do this. You can just do it right away. A harder way, you have real international things like a space station. CERN or ITAR, these are very hard to, multi-million dollars things. It's very hard. So I would say just stick to this exchange program. And finally, I was asked to talk about education and so forth. So finally, I would say, so common sense. We have many common sense that we discovered through science. For example, in the past, we have, heliocentric theory, Copernicus, gravitation and evolution by Darwin, and relativity, and finally we have this quantum mechanics came along 100 years ago. And all of them are not accepted at once. It took a long time. And people get killed also. So knowledge creation is by research, and knowledge spread is by education and public outreach to make these things, new scientific discovery, into common sense. And common sense were all not accepted at once. And quantum mechanics, which is our topics in this forum, discovered about 100 years ago, but it's not really a common sense yet. I'm teaching quantum mechanics. I teach like entanglement to students, university students, and they said, no, come on, it's not right. But, I said, this is right. But after many, many years, right? Nowadays, they kind of accept entanglement and so, but anyway, we need to work harder. And that's my last message. Thank you very much.
Yeah, thank you very much. So we'll have question after all 6 talks. Okay, the second speaker is Professor Yoon-ho Kim, professor here at POSTECH. Please.
Thank you very much. So I was asked to give a short talk about education. It's always a good idea to start with some unconventional title. So I would like to talk about quantum information education in a over-quantumized age. So what do I mean by that? So do I have this? So it is somewhat of a general knowledge that so-called first quantum revolution is based on quantum physics, but particularly energy quantization. So the people in the first row, they gave us transistors, and then the people in the second row, they gave us laser diode and integrated circuits. So all the communication systems, information processing systems, they are based on this. So if you look at the quotation for the Nobel Physics Prize in 2000, it says for basic work on information and communication technology. So if you simply put quantum there, right, it will be for basic work on quantum information and quantum communication technology. So that's sort of the idea for so-called the second quantum revolution, which in this community we often use that. And the basic physics there, or the basic conceptual ideas are entanglement and quantum measurement and so-called decoherence. And in particular, the gentlemen here, 3 of them, they recently received Nobel Physics Prize for entanglement, or the demonstration of so-called the Bell's inequality. So in quantum information, we believe in general that at some point in time, computers can function fully quantum mechanically, and then there will be some metrological applications where you will have quantum enhanced sensitivity, and at the same time, communication can be improved to a limit where quantum physics allows. So these are sort of hopeful ideas. Now, But nowadays, right, if you just Google a little bit, you will see all these wild claims. For instance, this is from some market research data. So it says here, top 10 game-changing applications for quantum computing. And you see drug and chemical research and battery technology and even digital banking, all that. And what I can tell you is that there's not a single mathematical proof that this will actually work, but they just make claims. But it may work out or it may not work out. Nobody really knows at the point. Probably that's why it makes possible to make all these claims. Another somewhat recently saw in a paper that I saw this figure in an archive paper over there. So it says a quantum warfare, right? Even the war has to be quantum nowadays. So you see that the quantum internet, and quantum underground mapping, and quantum inertial navigation, everything is quantum, right? So basically what's done here is that you take very well-known technology and then just put quantum on it, and then somehow it becomes quantum. And I reject this idea that this is possible. So what I want to talk about then is somehow we need to go through this overhyped era, and then we will need to build some expertise to outlast this hype cycle so that eventually we will have some technology. So what do we then need? So the fundamental concepts, right? Entanglement and measurement and decoherence problems. And then you'll have information theories, algorithms, and error corrections, and all this information resource theory. And then you also have enabling technologies, device engineering and material science. And then finally, you have physical platforms where you have atomic physics and quantum optics and condensed and solid-state physics. Somehow all these things need to come together. And then hopefully, in some 10 years' time, we will still survive in this field so that we can actually make a realistic progress. And hopefully, to be able to do so, at PostTech, we have a quantum information graduate program. And luckily, we were able to be funded by the government. So we have a PostTech-led consortium, UNIST and DIGIST, both of which are government-funded research institutes, and with 3 universities. And we have jointly a quantum information-oriented graduate school program, where we hope to achieve an interdisciplinary education in quantum information, and also. None of this is going to be really possible locally, and we have a collaboration agreement with A-STAL and CQT at Singapore, and we also have recently launched also government-funded and so-called global partnership program with Harvard and MIT, and hopefully we will want to expand this program to Japan and EU, perhaps in the coming years. So the overall idea, in a sense, is that if you like science fiction novels, right, you probably know Arthur Clarke, and he said some time ago that any sufficiently advanced technology is indistinguishable from magic, and I fully agree that. And I remember when I was young, this cartoon or anime appeared in Korean TV. It's called SF Sayuki Stajinga. In Korean, it's different. But this guy here always looks up information through his tablet, right? But that was 1978. And nowadays, everybody has one of those. It took some 50 years to get there. And I hope that it takes physics and engineering and a bit of time. And hopefully, we'll be able to get there as far as quantum information technology is concerned. Thank you very much.
Yeah, thank you very much. Next speaker is Professor Jin Yoon, who is the president of the Korean Physical Society. Please.
Thank you. I'm really happy, and I appreciate all the efforts for APCTP. You saw all the list, all the organizations who make an effort to make this event live. And so thank you for the organizers. And here today, I want to give the kind of activities done by KPS on the international research collaboration and public outreach activity. I think maybe you can consider my presentation as the example of the all the activities we can do for making the quantum science alive in our life. Next one. Okay. Maybe the United Nations, just after 100 years of opening of quantum science, United Nations recommends the kind of International Year of Quantum Science and Technology, but the important one is activities at all levels. It means, kind of increasing public awareness of the importance of quantum science and applications. And so the Korean Physical Society has done has opened several events so far, and so I will give you some examples we have done so far. Okay, early this year, in 2025 February, we had a kind of proclamation ceremony. Okay? And here the president of IUPOP has gave a congratulatory remark, and various people coming from very diverse group has participated this ceremony. And for example, Minister of Ministry of Science and Technology, senators, mayor, presidents of science and technology associations, and presidents of universities, press and cooperation, business people, all these diverse fields are very interested in the quantum science. And then for maybe about 2 or 3 months, our KPS has opened a kind of event that the physicists, we have a lot of members, and so they are participating their alma mater, and gave a lecture on quantum science. So these are maybe here you can see the list of the schools they have visited. Okay, for example, actually, I had myself visit my alma mater, and 120 students has participated there, and I supposed to give a 45-minute lecture and 15-minute Q&As, but can you imagine how long it continued? 2 hours after my lecture. So the students were very, very interested and very curious about the quantum science, actually. And so altogether, actually that 2,300 number, that is the number of the souvenirs we produced, we distributed, and but maybe more than 4,500 students has participated in this event, and it was proved that to be very efficient in advertising and outreaching. Okay, next one is during the Korean KPS spring meeting, we have a kind of event which plans the science meet art, okay, and collaborated with the IBS Quantum Nanoscience Center at UI University. And the objective is to broaden perspectives on how science can engage with art, and to illustrate how quantum concepts can become more accessible to the general public when reinterpreted through art. This is the one example. So, there is a kind of state, black and white, up and down, and something like that, which stands for the kind of quantum superposition. And the shape of the model is changing when you move from left to right. Then it means a kind of point of view. The state depends on the kind of observer's point. So it is it really it attracts the interest of participants of KPS, and so around 600 visitors for 2 days. And they showed continuous interest throughout the event. And we really appreciate the intuitive and artistic approach to complex quantum ideas. And it really engaged the new dialogue between science and art. And this is the photo booth for young generations, I mean young participants. But figures you can see here is not young that much, just because I am the one who possessed the pictures. Sorry about that. But anyway, young people really like this photo booth, and they got a lot of pictures. And as you can see, the Schrödinger cat in the box. And so this was very interesting. And we have especially focused into the quantum science in several sessions and symposiums and tutorials and the kind of things here in last spring meeting. And also we will have another this coming fall meeting at Gwangju. Also we will have one plenary lecture by Peter Jolla, who is research director of Institute for Quantum Optics and Quantum Information of Austrian Academy of Science. So if you have time, and please come and join. The next one is actually Yonsei University who held this IIQ global event titled Communicating Quantum Science and Technology to Public. So there had been 4 sessions, and as you can see from the title, it is mostly focused on the kind of communications, the title here. And this is the picture, and we really actually, physicist is very weak in communication, so with the public especially. And in that sense, we get a lot of lessons and tips from media and all panelists. And early this month, I have participated the United Korea Conference at Atlanta, and there, this event is for the future U.S., of course, U.S. and Korea, advancing science and technology to benefit humanity from Earth to science. And there has been several signature forums, including quantum computing of there. And I myself make a presentation at the Joint Science Policy and Diplomacy Forum. And we have discussed with the international collaboration between Korean part and the Department of Energy in U.S. Lastly, I want to mention that we will have an APEC forum this fall at Gwangju during the KPS period. And there, actually, we have the goal of there, so to foster regional collaboration on quantum readiness and to unite academic and research leaders to bridge technology gaps and to implement initiatives such as educational programs, facility mapping, and knowledge database. And we expect the impact to get the equitable access to quantum advancements and to strengthening the region's global competitiveness. This one is composed of 2 keynote speeches and 5 sessions. From the title, you can see the current and the future of quantum science and technology, educational programs, research facilities, and the international cooperation. And finally, the last topic is open and will be called for next 2 months. Okay, and this is the last one, and KPS actually, we are planning, and we have done several events to attract and maybe outreach the quantum science to the public. And KPS of the history of 73 years will open the road for the scientific communications to our future generation. Thank you.
Thank you very much. Thank you. Next speaker is Sang Yoon CEO of ID Quantic. Please.
Good afternoon. Good afternoon. Yeah. Thank you for having me here. I think I am the only non-physicist speakers in this forum. So please enjoy the non-physicist point of view, especially the industry perspective. I think this is a very rare case to ask me to talking about education. In most of the cases, the people are asking me about the technology, engineering solution. What is the use case? How we could experience the quantum technology? But this time, a little bit different. But I have to introduce my company first. Is one of the obligation to the public speech. Sorry, but I will try to keep it very short. ID Quantic is founded 2001 and spin-off from the Geneva University. I think that's one of the reasons why the organizer asked me to talking about educations. The physicists, theoretical and experimental physicists combine together to prove their theory to measurement and show the data. That's how come the company start from 2001. And 2018, Korean telecom company SK Telecom invest to the ID Quantic to show and deploy the actual product to their 5G network and mobile infrastructures. That's how we started. Yeah, you know, still the quantum industry is very early stage in the industry-wide. So if we do anything, that might be the first come in the world. That's how we are starting. World first quantum random number generators, and we deploy the first QKD in Geneva election networks. And then 2022, maybe some of your parents are using Galaxy Quantum mobile phone series. This is very competitive mobile phone because without wireless charging, most of the features are very powerful. So this year, 2025, we also launched the Galaxy Quantum 6 in the market. So education, why education matters for industries? In our company, there are two different species, physicists and non-physicists. We call it the engineers. They are fighting each other every day. I mean, in constructive ways to prove the opinion and argument based. I think it is good because the bottom up, you know, the thinking ideas and trying to resolve the real life challenges. That's how we come to deliver and improve our product. Okay, I think the skills interdisciplinary knowledge becomes not only the physics. We need quantum science, the computer science and network security and problem solving for market-ready solution. Most of all, to sell the product, we have to comply to the standard, global standard and the certification as well. So based on this kind of the common knowledge, we have to prepare our knowledge transform to the real life working products. That's why the education is matters. But there are talent gaps, especially when we try to proceed the real life application to the telecom utilities, financial customers. All these kind of the domain, each of the domain has a specific user demand. That's a really big gap in between theory and the practical domain knowledge. And also the shortage of engineers in both the theoretical and practical skills. I think that this kind of challenge is not only Korea, but also the globals. So one of our internal practice, whenever the newcomers are joined on board, we do not only the general training, but also we have the regular education and training course. If the physicist, we do for the engineering. For the engineers, we do for the quantum theories and more the theoretical background. So in this kind of the exercise could reduce gap in between engineers and physicists. So current engineer education gap, in the industry perspective, university programs are still theory heavy. I think the things are improving, but still most of the curriculums are theory based and heavy relies on the job training. So I think that there are some good examples from the global experiences. US has NSF Quantum Leap, and also the big giant quantum computing company, IBM, Kiski Summer School. IonQ also have the similar. Also, the EU has Quantum Technology Master Program. We also, our company has the Winter School Program. So I think this kind of activity shows how to reduce gap in between the academia and the industries. What the industry needs, we want to make a joint curricula between university and companies. So more focusing on the problem solving based on the real life challenges, and more engagement for the standard and policy education. And one of the good examples is a recent NIA, the quantum internship. This shows one of the intern awarded the first prize. If some of the students trying to experience of not only the theoretical training, but also hands-on, real life, the product hands-on, you can apply to the NIA's, the quantum internship program. So based on these more hands-on, commercial grade, actual quantum equipment, and learn industry level reliability, compliance, and integration. I think this kind of the activity is value for industry, job, and entrepreneurship as well. So how we can work together? Thanks to the Korean government great initiatives, we already have the 3 quantum graduated school in different regions in our countries. So I think this is good. But I think more than that, we need industry demand-based curricula is required. So I believe the industry doesn't stay just a consumer of the talent, but also we want to contribute what actually we need from them. So joint platform, I think in this perspective, APCTP could contribute, university, research institute, industry, and government could collaborate together to make a neutral hub for the talent gap for the quantum technology. We also contribute a partnership with hardware, software, and workshop together. So partnering gives access to real-world quantum devices. So we also could working together for the joint lab modules, simulating deployment, and co-branded certification, and field internship with the operation system as well. So this is my closing moment. This is one of our unique product, the SNSPD, superconducting single photon detector, nanowire single photon detector. Sorry, it's too long. Anyway, it's well known. Collaboration from the academia industry, and many of the industries are using this product to test and measure of the quantum phenomena. So I think industry must co-design education, not just consume it, and bridging the gap between research and deployable solution together. So I'm looking forward to discussion further, and hope to enjoy. Thank you.
Thank you very much. Yeah, next speaker is Long Chuang Quack, and we need a little time for preparation of the view graph. Yeah, so during the time I can introduce you. I have a time to introduce you, so you make it. So. Yeah, so he is now the professor of Nanyang Technical University, Singapore, and also the National University of Singapore. And although he is a very important person, so he is the chairman of the International Committee of the ASEAN, how says it's a Physics Olympiad, right? Yeah, so next, yeah, he is. Yeah. Oh, really? Okay. So, yeah, former president. Okay. So, okay, ready. Okay, thank you.
Thank you. So I know many people from Korea since I've been here many times. And I think, okay, I'll keep it short. So this year is the International Year for Quantum Science and Technology. I knew the process because I was a member of the International Union for Pure and Applied Physics way back when they were proposing it. It was actually initiated by the American Physical Society. So here I show a recent quantum computer that we have acquired. So the fridge is actually built by us, module by modules, so it's not entirely imported. And that was a very old chip, something like maybe 15 years by now. And I'm pointing there, pointing here. Oh. I see. So from there you can see that if you magnify that, you will see this Batman logo, which is with the CQT on it. But it's just a 10 qubit chip. So what I'm talking about, I think this is not what I'm talking about. It should be the other slide. This I will talk about later on. This is not the slide, it's the forum one. So this is actually the forum one, but anyway, it doesn't matter. Thank you. Yeah. Thank you. Oh, I need. Okay. So alone we can do little. Together we can do so much. Actually, so much more. This was you have seen that Helen Keller's. Helen Keller was a very famous novelist, American novelist. I think she should get the Nobel Prize in Literature, but she didn't, I think. And I think she has written many books, in fact. If you search the literature, there's a recent paper by Marek, almost my name, Quack, with an I. So he sees more. He has an I in his character. 2021 study published in the Studies in Higher Education. And he's from Poland, of course, from Poznan. And he said that the study reveals that overall research output in Europe has increased, and this growth is primarily driven by international co-authored publication, particularly in major European systems like France, Germany, and UK. So basically, he's stressing that it's important to have international collaboration. So these are hardcore data that social scientists have compiled. And over here is The black one is very high international collaboration or co-authored publication, ICP. And you can see Germany, including United States, are all very dark colored. Also, the whole of Europe is very dark colored, including, of course, the rest of the world. You see Africa, which is very brightly colored. And I think it is one region that we need to work on internationally to engage Africa, as well as the big chunk over there, which is Russia. Russia, unfortunately, is now at war with Ukraine, but nevertheless, it does affect its own international collaboration. Critical research finding has shown that international collaboration needs trust. I think this is taken for granted. We need to prepare students, faculty, researchers for international collaboration. We need to create a room for post-assessment as well. In terms of partnerships, I think international can exist as a partnership. It can also exist as, like in this particular case, conferences and symposia, forums, and also to a large extent, but this should not be overemphasized, MOU, Memorandum of Understanding. So I think, 감사합니다.
Thank you very much. Last speaker is Professor Misao Sasaki, President of APCTP.
Oh, this is okay, hello, good morning, and not the morning. In the afternoon, I'm a bit confused. Anyway, so today I'm just summarizing what we are doing here, so not necessarily on quantum science. Actually, as I have written in my opening remarks, the theoretical physics is essentially the core of this quantum science. And most of the theoretical physics are based on quantum physics. However, we are actually using quantum physics to explore the laws of nature, but not necessarily, applying that to, say, understand the implications of quantum physics. And so today I'm hearing a lot of all these talks and presentations, and learning a lot. And we hope we will expand our sort of visions to include all these interesting quantum science things. Anyway, today let me just introduce what we are doing and what the current situations are and so on and so forth. Which one? Yes. So first of all, this APCTP is established in 1996. So next year is the 30th anniversary. It was the first president was the Xian Yan, a famous Nobel laureate in particle physics, and we have about 19 member countries and regions in this Asia Pacific, and essentially this is endorsed by the APEC, and which is the reason why we are having this forum and symposium in commemorating the APEC meeting this year here. Yes. Okay. So as far as the international research collaborations are concerned, that we are doing. Of course, this is as a kind of a resonator. I mean, we are to have the international collaborations, and as you could see that we have a lot of visitors from abroad. And approximately we have 5,000 visitors, and half of them are from outside Korea. So it is really the international place. And as far as the education research is concerned, we have a very nice system of a mid-career scientist. We call it junior research group leader. And this junior group research leader will have sufficiently, I mean, for us, it's enough sort of funding and also the resources to hire a couple of postdocs, as well as to do many international meetings and so on, hold meetings and so on and so forth. Anyway, so we have about 10 or 11 JLG leaders per year, and they hire approximately 2 each. Each leader has 2 postdocs, so 22 junior research group fellows. And we are doing quite well, as we see this from the data that this group, this JLG, is established in 2008, and in total, so far we have 159 alumni, and almost 80 or 90% of them got their academic positions afterwards. And also, by the way, yes, this is another important thing. Thanks to the cooperations with the POSTEC. POSTEC actually is the most important organization for us, because they are giving us a place, this building where we are based. And also they are happy to have some this collaborative educational system. So, and especially this junior research group leaders affiliated with POSTEC, and some of them actually give not only sort of informally mentoring students, but formally giving some courses, lectures. We have this young scientist training program where we call many applicants from this Asia Pacific regions and let them stay here and experience what the research is actually. And actually we have quite talented young people, and they also, after this, most of them will get the academic positions, usually the postdoc positions, because they are young. But anyway, they continue to do research in our field. And we have some for, these are for the young people, but we have APCTP Associate Fellow Program, where we invite a middle sort of a career scientist to come to APCTP and they talk to those young people, and then discuss and possibly enhance the collaboration and so on and so forth. And this is going very well too. We also try to connect to the public, so that they are, we can expand our sort of hemisphere. And one of the most important sort of activities is monthly published web magazine called Crossroads, and it seems that this has been quite, as you could see, popular among those people who like, theoretical physics. And also we have this APCTP Science Book of the Year, and we choose 10 best science books, and also then asked students to write some essays about those books and so on and so forth. And we have several interesting sort of programs, like a book essay contest, and some book, though I don't know if my pronunciation is correct, this youth science essay contest and so on and so forth, and so that the young people, especially high school students perhaps, can join these events and enjoy what science is. We have some science in City Hall collaboration with Pohang City, and we thanks to this collaboration with the city Pohang of Pohang, we have interesting sort of connections with the public people. Okay, and so these are the things we have been doing, and then of course as I said in the beginning, since theoretical physics essentially is the core of the quantum science or the quantum physics, if you have, from the point of view of basic science, we are really doing good. But apparently this is not enough. And in these days, we are facing, some of the, or maybe many of the those presenters today said that we are actually our society is now experiencing new kind of revolutions in quantum physics, and which has become very important. So not only to sort of enhance our research activities, we do also need to go into this quantum science thing. And for this, of course, there are so many things to do. and we are having all these new sort of programs we have in mind, but oh yes, I see. Now I finally knew how to use it. So as far as this quantum physics or quantum information is concerned, so we are just beginning to recruit GLG leaders in this area, and as soon as we get somebody who is good enough, then we will start having the YSD fellows. For YSD fellows, you need some mentors, and at the moment, of course, our current GLG leaders can be the mentors if they want to do some quantum science, because they have talent. But as you could probably imagine, that those people, including myself, theoretical physics, usually are interested only in theoretical physics and not much on those implications of theoretical physics. So we do need somebody who wants to do such things, and hopefully within a year or so we have new leader coming and expanding to this science. Thank you very much.
Thank you very much. Yeah. So I think you have to be seated here. Okay. So we have 6 speakers. Please be seated in front. President Yoon is, I think, here. Yeah.
That's a name.
His name? No. It's this kind of.
Well, I should probably stay.
Yeah, you're here. Yeah, you are on this side. So, yes, you're here and here. Okay. So we have some questions from the audience, if you have. So any questions in the audience? Okay. Yeah, please. Mike.
Hi, thank you so much for the talks. I am a researcher from APCTP, working in quantum gravity group. So I have 2 brief questions. I think Professor Misao already mentioned something about like non-AP region. I am from India, so I wanted to ask, how does APEC include scientists from non-member countries like India who are working as and doing research in APEC countries? So, and what are the opportunities that APEC creates for non-APEC countries researchers? Thank you.
Sorry, I don't know what these APEC countries mean, but we are Asia Pacific Center. APEC endorses us, but it doesn't mean that we have to follow the APEC's, system or the regions or anything. And so in that sense, it's really the Asia Pacific regions, and which includes India, of course. Yes, I don't know. Is India part of Asia or not?
India is not formally part of APEC, right?
No. Forget about APEC. APEC is nothing to do with us. I'm sorry, it's a bit of too much saying. As far as the organization, our organization is concerned, APEC is nothing to do with it. APEC endorses us, and APEC supports us, but it doesn't mean that, it's like Korea supports us. I mean, Korean government is the most important supporter for APCTP. But we are not just doing physics for Korea, but for the international physics, right? It's the same thing. APEC may support us, but our activity is not limited to APEC countries. Yes.
Okay, thank you.
Sir, I just want to make one comment. Maybe push your society to join the membership.
Yeah, I think that the India is a member of APCTP, right? Okay, so it is. And also India is the member of AAPPS. So you have all open opportunity.
Yeah,
okay.
Thank you so much.
Yeah. Any other question? Yes.
Thank you for the great talks. As you know, I had no reply from the Professor Pan in a few minutes ago. So I asked the same question to all members. Yeah. I wonder how promising the quantum science technology is for not only for the college student, but for the secondary and primary student. I mean, if I
so the first primary means the elementary school, right?
Yeah.
Elementary school or middle school or high school.
Yeah.
Okay. Is anybody can? Okay, please.
Okay, maybe I could give some comment, since I'm non-physicist and my background is engineering. I majored in mechanical engineering and then computer engineering. And over 20 years, I worked for the German company not for the engineering, but the business. And then I joined to this ID Quantic, the communication companies. And at that time, most of the challenging was trying to understand what is the quantum physics and quantum theory and how to combine between quantum technology to solving the real world problems. So I somewhat struggled at that time, and in many cases, people are asking me about pitching about the company technology, and at the time, people are asking first what is the Schrödinger's cat theories, etc. But after 5 to 6 years, then I can see many of the public, the YouTube, the television, talking about quantum physics already, not only the Science Channel, but also, the comedies or the live, the channel also mentioning about the quantum technology. And this is how shows the quantum technology was already transforming from the academia to the industry. And that's why I moved from the previous big global company to the quantum startup. So I believe the quantum technology innovation could deliver more actual problem solving to our real life solutions. So I'm more confident than, I don't know, maybe the physicists, maybe in industry perspectives. I believe the quantum will be more crucial to transforming our actual real life solution. Yeah. Thank you.
Yeah, thank you. So anybody can? Okay.
Yeah, maybe I can add something that it's very good that not physicists, one engineer answered the question. Usually scientists do not have imagination enough. For example, when they're transistor was invented in Bell Lab, they tried very hard to replace vacuum tube, but finally they got it. And then Bell Lab said, people ask, what can you do with this transistor? And they think very hard. And maybe they said, oh, maybe it's very good for hearing aid. Okay, this is that, you know. And also IBM, finally they got this, I forgot the series, this computer in maybe 60s. They said, IBM said, maybe you need, in the world, maybe 2 computers. And computers used to decipher code and also calculate the ballistic trajectory, and that's all. But nowadays, everyone in your pocket, maybe you have 2 computers. And it's very hard to predict the technologies, and especially for a researcher, for us, you know, we cannot really predict. But it's really new. Quantum mechanics is fantastically new, and what can this do? I think, and maybe user knows better. This is my comment.
So do you want? Okay, it's then. Yeah, please. Yeah, you first. Yeah.
Okay. I just want to clarify, add to something that is currently being done in Singapore. So I sit on the committee to incorporate quantum physics into the secondary school curriculum. So I note that is secondary school. But on the other hand, there are avenues for engaging primary school students. The sort of events that I'm talking about are informally through science centers activities. So the science centers do tap on us to organize exhibitions. And I think this is basically to enthuse primary school students to the fascination of science. They may not entirely understand what is quantum science, but never mind, it is an experience. After all, even if you have given them very basic science about energy, it doesn't mean that they fully understand it either. So it is an exposure. So through that exposure, if and especially if there are hands-on experiments, they get enthused, and eventually they like science, and in particular quantum science. I hope that answers the question.
Yeah, please.
Actually, I agree with all speakers, but I just wanna make one point from a different view. Actually, quantum science, maybe we cannot do anything without quantum mechanics or quantum science from now on, maybe for a long time. But what I want to say is, okay, for a primary school students, maybe they are getting a job after 10 or more than 10 years later. 10 years ago, we didn't know this quantum science is really boosted up like this. So after 10 years, nobody knows. And the important thing is, in a basic science, it should be prepared, get prepared for everything, I mean, every coming futures. And so the diversity is very important. And I just want to focus that one saying from Chen Huang. He said that if he is born again, then he will do the physics. That means I just emphasize that basic science is very important for the future generation, not just the quantum mechanics, but for everything. That's what I want to say now.
So I'll just show you an experiment. So I carry toys with me whenever I go around selling science. and this is one toy. Now this is called the tippy top. Why do I bring this up? Because if you Google, I don't have the picture, but if you Google for tippy top, you will see two quantum physicists looking at this tippy top. Actually, it was Niels Bohr and Wolfgang was Pauli. And in fact, what happened is I wrote this. But science is all about this. Do experiment that fail. And the reason why you have to show science experiment that fail is that do again. This is Teletubbies message. So at some stage, if you do it right,
Yes.
at some stage, if you do it right, then it stands up. And then, of course, the question you can ask little kids has nothing to do with quantum physics, but what happened? How did this tippy top move upright? I leave you to think about it.
Yes, because time limit. If you have a question, the short question. Okay, if not, okay, yeah.
Thank you for sharing a lot of inspiring the thought about education, also international collaborations and so on. I'm just particularly interested in Singapore's aspect. To me, nowadays the world looks like dividing two sectors, but somehow Singapore is very good friends with the US side, also very good friends with the China side. So I'm just wondering how, in general, people think about it and so on.
Yeah, I do not know how I think about Singapore, but certainly we want to portray Singapore is a very, very tiny piece of land, so tiny that it's even smaller than Seoul. So in order to survive, we cannot make enemies. If we do have to make enemies, we must make two, at least two, so that the enemies will fight among themselves. So we can't. We simply cannot afford enemies. So what we do is that our strategy is to make friends. And of course, in the international, the geopolitical situation currently right now, there are lots of tensions. And how Singapore deal with it is to make sure that we are friendly with all the people who are at tension. However, we will not commit to anything that is of detrimental interest to Singapore. For example, in the Ukraine situation, we'll support Ukraine simply because Singapore is a small nation and we encourage Russia to attack Ukraine. Then all the neighboring countries which are larger than us will attack Singapore. So we have to have certain principles at stake. So there are certain principles that we have laid down which are instrumental for Singapore's survival. And aside from that, we try to make friends.
Okay, so because of time limit, so I'd like to thank all the 6 speakers again. Thank you very much. So how many minutes do we have a break before? Okay, so you do. Okay.
Okay, so thank you again for the insightful discussion. So before we proceed to the next session, the symposium will take a short break until 4:05. So please be seated by 4:05. 네, 저희 다음 심포지엄까지 4시 5분까지 휴식 시간을 갖도록 하겠습니다. 방문해주신 내빈 여러분들께서는 4시 5분까지 자리에 착석해 주시면 감사하겠습니다. 곧이어 심포지엄을 시작할 예정이니 방문해주신 내빈 여러분들께서는 자리에 착석해주시기 바랍니다. We will soon begin the symposium portion of the In Commemoration of APEC 2025 APCTP Forum and Symposium on Perspective Quantum Technology. So please be seated. 네, 한 번 더 안내 말씀드리겠습니다. 곧이어 심포지엄이 시작될 예정이오니 방문해주신 내빈 여러분들께서는 자리에 착석해주시기 바랍니다. To begin our symposium, it is my pleasure to invite Professor Long Chuan Kwek to present his talk title, Integrated Photonic Circuits for Quantum Science and Technology. Please give him a big round of applause.
So I guess I've explained this, so we can skip this and you already know that it's International Year of Quantum Science. So let me first go very quickly through. I try not to be too technical. I'll skip through the technical part if I can. So why integrated photonic circuits? Well, simply because on a nice bit you see sand. Okay, and sand is the basis behind silicon. Now, silicon has very nice properties, and I'll not elaborate too much on the technicality. But more than that, we also want to use light. Silicon allows light waveguide to be carved onto the chips, and therefore allows light to interact with matter. And integrated electronics, therefore, make full use of these electrons, but integrated photonics makes use of photons. So that's the first point. And electron move very fast, but so does light. And the other thing about light is that it is the capacity. You will see that light is capable of what's called multiplexing. So it can carry a high bandwidth and therefore carry more information. Now, but electrons, of course, can be entangled. They are metals, so they can talk to each other. And I've not explained to you what's entanglement. It's a strange concept to some people. But photons can actually do not interact. So this is a big thing. Photons do not interact, not like electrons. However, they can do something. They can get entangled through crystals. And then when you get photons entangled to crystal, it's as if you flip a coin that is fully correlated, even though they are separated miles away. So this is just an analogy. In some sense, it's what Einstein called spooky action at a distance. So if one coin flip head, the other coin will flip head. Okay, of course, it could be head and tail in some cases. But there is actually no real information passed between the two parties. In this case, we call it Alice, and the other case, the other part is Bob. Simply because you never know or never realize what sort of 0 or 1 you're going to get. And in fact, this sort of entanglement was first established by Wu Jianxiong and Ivan Shaknov, way back in 1940s. So what they did was an experiment in 1949 where they showed that they could get photons entangled through a crystal. By now, of course, it's history. Sharknov is interesting because he was a spy in Korea. And he was killed somehow, unfortunately, but he was a very promising scientist. Now, the other person who did experiment on how to entangle photons was Kocher and Cummins in 1967. So Karl Kocher has always been pushing for his Nobel Prize. He didn't get it, but nevertheless, he did one of the earliest experiments. The Nobel Committee actually asked me about this experiment. And I said, well, it's still not up to par yet. Clauser and Freeman did another experiment. Freeman has passed away, but Clauser is still around us. When I first met John Clauser, he was carrying a typewriter. So he is a very old-fashioned person. He carries typewriter, not computer, everywhere. Maybe not nowadays, but when I saw him 20 years ago, he was. And so the next experiment to get photons to talk to each other was by Alain Aspect, Granger, and Philippe Granger, and Roger. And what they did was a Bell experiment, a Bell inequality experiment. You heard Jianwei's talk earlier on how China has geared up to prove Bell inequality. We'll come back to that. But Bell inequality is an inequality that established that says that if you violate this inequality, then you have quantum particles talking to each other through quantum means. Violation of Bell inequalities were therefore done, and it gets longer and longer. And even in not just photons, it was also in ions, which I think Kiwan will tell you later on. And also in assuming gravitational induced collapse over 3 cities that are separated quite far away in Europe, in Switzerland. And also in superconducting system with John Martini's group at that time. And then, of course, there were proposals going beyond the outer space and measurement of cosmic Bell test. That has not been done, but we saw earlier on, this is the schematic diagram of how cosmic Bell testing experiment can be done. I'll come back to this slightly later. And of course, Jianwei mentioned earlier, he has also done experiment over 1,200 kilometers through satellites. This was one of the early experiments. You saw this subsequent experiment between Urumqi, Delinger, Lijiang, and Nagari, as well as Beijing, and collaborations with Germany, Italy, Russia, Singapore, Sweden, and so forth. And recently, of course, they have been collaborating with South Africa. Hansen also did an experiment on by over a very short distance for electron spin. Actually, it says 1.3 kilometer, but it's on the chip. And then we have detection of entangled atoms. And what do we do with all this property of so-called entanglement? And one of the things about entanglement is it allows you to transmit. If one party measures a 1, the other party gets a 1. If one party gets a 0, the other party gets a 0. Basically, the two parties establish common rubbish. Now, why is common rubbish important? This is a trick not of quantum theory, but it's classical. So quantum theory sometimes need classical science. And in classical cryptography, or communication, it turns out that if you have common rubbish, then they can both establish a very secure key. So that common rubbish serves as a key to unlock your information. And one of the most important things to think about common rubbish is that 0 plus 0 is 0. 1 plus 1 is also 0, modulo 2. That tells you that rubbish plus rubbish is 0. You are not adding anything. So you have a message, you add rubbish, you send it over, you add another piece of rubbish. Rubbish plus rubbish is 0. You get back the message. So that's the key idea. You can access YouTube with Alan talking about his experiment. I'm not going to play this video, but you can get it. And what we did at some stage was that we decided that perhaps we can scale it down even further. Not that cryptographic sets are very big. Nowadays it comes as 1 foot, 1.5 foot by maybe 1 foot box, and maybe half a foot height. And we decided that maybe we can send communication through a silicon chip. So that was the start of why we went into silicon photonics. And so we performed, there were many experiments done, but what was not done on the chip was a continuous variable quantum key distribution. So that was when we first started. And we published our result. And one of the important things about continuous variable quantum key distribution was that it was compatible with telecom communication. And in this particular instance, our original objective was that since our phone, our handphone, contains hundreds, if not thousands of applications, adding one more application does no harm. By this addition of this extra application allows little kid to play quantum key distribution without knowing what is quantum key distribution. Why is that important? Because if they find it useful, they will invent new ideas based on that. And that was how we thought a lot of these inventions could be done. So I'll not skip the details. Adding one more chip involving a photonic chip wouldn't harm. Okay. So I'll skip that. And then we went on to perform another experiment, which was called MDI-QKD, in the midst of COVID in 2020. So I'll talk to you a little bit about something else that I did in 2000, and that was switching gear a little bit, is a biological experiment where we look at rats, and then we induce cancer in the rats, in the colon of the rats, and then we insert optical fiber through the anus. And this is the optical fiber, it's very rough. And then these are the colon, swollen, and these are the cancer cells. So what we did was that we have rats, we shine laser light on it, and then we extract the cancer cells. And we find that by looking at the reflected light, we could actually diagnose quite well, not 100%, malignant tissues. But at some stage, we decided, hey, at that time, this clearly was around 2000, 2005. So it was the early days of AI. At that time, in fact, this was when AI went down the hill. People were disappointed with the ability of AI, but we could show that artificial intelligence could be used to classify these cancer cells as well. I don't want to give you the detail. Now, so what exactly is artificial intelligence? It is a neural network, and why do we call neural network? Is a whole series of net shown up there, up front, in the top left-hand corner. And in principle, on the classical computer, each node is linked to the next by so-called weights. And at the end of the day, the output port is a linear summation of all these weights with the input. And what we saw was that this exactly mimics the classical chip that we were designing, except that we could tune our phase shifter by heating, and then the heat that we apply to the phase shifter acts as the weights in the original neural network. But what was important was that our phase was actually not just a number, but something called a complex number. A complex number is, of course, carries more information in some sense. And we were able to show that with artificial neural network like this, we could classify classical data. And we did it, of course, with various designs. And the chip doesn't have to be very big. 8 input port and 8 output port was all you need. And then we start to train chemistry data, and we got a pretty good regression score. Okay. So what else can you do with integrated photonic chips? Well, Tian Wei mentioned earlier on about boson sampling. Now, I did give a seminar earlier on, but it was a technical one. But in this case, what was important was that boson sampling is a specific algorithm that allows you to say that if you now do boson samplings with light, then that experiment has an advantage in terms of computing the probability experimentally. That probability has a lot more advantage than a classical computer. And so typical boson sampling starts off with various combinations, output combinations. So imagine that you have 8 input ports and 8 output ports, and you allow 2 photons to come in. Then the 2 photons can go out in any of the 8 output modes. So you can list out all possible combinations. In this case, we have 16 output. This was an experiment done by Jian Wei. And the bottom, which is the theory, and the top is the experiment. So this is wonderful science because it is a pure work of art. It is the teddy bear and his mirror image. They look alike, hopefully. And then it was shown that if you want to do boson sampling, you can go beyond a certain photon number. So another system called Gaussian boson sampling was invented. And subsequently, we made use of that to do what is called predictions of Frank Condon factor. Never mind about that. So this is the same diagram that you show, that you get earlier on, except that it's a formic acid. The theory is above this time, and the experiment is below. So you see good fit between theory and experiment. I'll skip that. And then what can you do? You can also do autoencoding. And what's autoencoding? Is a chip that allows you to reduce the dimension of the inputs to a smaller dimension in the output. Now, autoencoder, it turns out, are very important for AI nowadays. So, but this is based simply on light, in some sense. And there are some results that shows how good the autoencoder, as long as the noise is below a certain level. And so we used the autoencoder for one purpose, which was called quantum teleportation. It turns out that at low dimension, teleportation is very efficient, but at high dimension, it's not. So we take a high dimensional data, squeeze it down to low dimension, and then teleport across and recover the information. And that fidelity is much better than working with the high dimensional state. We have also done this with cloning. Cloning is obviously very bad when you go to higher dimensional states, but we're not talking about exact cloning, but we're talking about proximate cloning, but still it is bad with higher dimension, so we did the same trick. So that was the chip, and that was the experiment, and That was a publication, I think. And more recently, we have also done integrated photonic chip for something that is more quantum in nature. It's called quantum superdense coding. The nutshell of superdense coding is encapsulated in 2 dimensions, although we did it for high dimension, in the sense that it is also a compressor of some kind. So we make use of quantum data as the input to realize this 8-dimensional quantum superdense coder. So these are the output results, and that's a publication. I'll skip that. Those are the details. I want to acknowledge the international collaboration that we have both locally, nationally, and internationally. You will see that we have collaboration with Caltech, with Tel Aviv, with Imperial College, with CDU in Hong Kong, with PolyU in Hong Kong as well, and with SUSTEC. So international collaboration at the end of the day is absolutely necessary for a good project. Thank you very much. 감사합니다.
Thank you, Professor Kwek. So next, we're going to hear from Professor Yuno Kim, who will speak on toward quantum-inspired classical technologies. Please give him a big round of applause.
Thank you. Clearly, I made a mistake. Sorry. So, I don't really want to talk about, let's say, quantum technologies here. I want to argue that at this point in time, it is more important to talk about so-called quantum-inspired technologies, where you borrow ideas from quantum systems or quantum correlations, and you try to apply to classical systems in an emulation scale. And sometimes it gives you better result than, let's say, previously available methodologies. So I'm convinced that this is the way, at least for now, and I hope that I can convince you a little bit toward that direction. So the idea here is sort of based on the fact that you have heard for some time that quantum information can or may lead to quantum computation and quantum metrology and quantum communication. But there's a may, right? It's not going to be for sure. So the cornerstones of this so-called quantum 2.0, entanglement and measurement and decoherence, these are all intertwined. You cannot really separate them. But we want to focus on entanglement here because it's sort of at the basic level, this is going to be the resource for quantum information processing. So entanglement is sort of touted as some strange effect, but it's nothing more than quantum correlation. It can be very simple. So here I'm showing you the most fundamental quantum correlation that we often talk about. And in 2022, this gentleman won Nobel Physics Prize for showing that there is a violation of Bell's inequality. But what does it mean, right? It sort of comes from the fact that you think about nature in terms of locality. So if you have a particle here, right? The idea, the common conception is, common agreement is that somehow the particle's properties are determined locally by local parameters. And everybody can agree on this, that this should be the case. But it turns out if you have an entangled state, there are certain differences, the observable differences. And that sort of is manifested in the Bell's inequality. So this wasn't really all that straightforward in that sense. Some years ago, if you Google it, you can find this interview of Murray Gell-Mann. So I'm not really showing the video here, but he says that the widespread foolishness associated with the EPL Bohm effect and experimental confirmation of quantum physics, it has to do perhaps with the fact that John Bell introduced words that are sort of prejudicial, like non-local. And when the quantum mechanical predictions were fully verified, I would have thought that everybody would say, great, and go home. But then instead they say there's something seriously peculiar here. So very, very critical. It's kind of understandable because he has his own interpretation of quantum physics. He also has a book about it. But nevertheless, in a sense, entanglement is not that strange, right? So it's a sort of good practice to compare entanglement with classical correlation. So you have a quantum correlation that with let's say 2 qubits. And then you can also think of a correlation between 2 classical or quantum systems. And one example that John Bell used here is the cartoon for Mr. Buttleman. So this guy apparently wears a pink sock and then not pink sock every day. So the idea here is that if you look at him wearing a pink sock on one foot, and then the other foot has to be different color, right? And this is a correlation, and you know immediately, right? It's a sort of a faster than light correlation. But nevertheless, this is purely classical. And it turns out entanglement is a little bit different because this is sort of a simple correlation. And then you can build a much more complicated correlation, all based on classical, let's say, local properties. So those are called separable states. So the idea in quantum information, one of the most important ones is so-called LOCC, so local operation and classical communications. So let's say you have Alice and Bob separated, and then Alice does some local operations to her qubit, and Bob does another kind of local operation to his qubit, and then they communicate each other, and they can prepare some, let's say, somewhat complicated joint quantum system. And this joint quantum system will satisfy the so-called separable state that's written over here, because all the properties are determined by local probabilities. And very strangely, there is an entangled state that cannot be written in terms of a separable state. And the key here then is to experimentally verify whether such an entangled state really exists. And it turns out from 1970s, people have been able to confirm this over and over again. And the idea of a loophole mainly comes from the fact that if I have 100 pairs of particles, and if I'm only detecting, let's say, one of them, maybe the others are maybe satisfying locality. So that's why detection probability became a very important problem. But nevertheless, classical correlations can be very complicated. Now, if you have an entangled state, and then if you add white noise, and eventually you can get to a situation where correlations can be completely classically expected. And this level of correlation, or quantum correlation, is related to so-called the Bell inequality violation. So for instance, if the Bell inequality is, let's say, violation is larger than, in this case, 2, then non-locality is, let's say, proven, although this may be an incorrect word. But if it's below that level, there's an entanglement, but Bell inequality or non-locality cannot be proven. And then there's also a level where these correlations are completely classical, and this is, in this case, it's a separable state. So there's a wide class of correlations, some classical, some non-classical. And the question then is, in an interferometry or in an experiment, all these correlations are essentially based on or observed in a correlation interferometry. So if I have a classical correlation, if I have a quantum correlation, and the level of difference, as you can see in this, the figure on the right, the difference is actually quite minimal. It's not that big, but it turns out this difference actually gives you a whole different effect. And in the kind of experiment that you do, quantum interference and classical correlation, they give you pretty much the same kind of data. And the only difference is, for instance, in this case, how low is the lowest point? Does it go to completely zero? giving you the maximum visibility, or it doesn't really go all the way down to zero. So typically in an experiment, that's the only observable difference. So if you then correlate this to a violation of Bell inequality, and there's a quantum correlation that actually gives you this non-local correlation, but there's this level of classical correlation. Perhaps this is still useful. It's not really quantum mechanically meaningful, but it can be quite useful, although it's a classical correlation. So that's sort of the idea. Now switching gears, right? So I want to apply this sort of a classical correlation to a meaningful, let's say, measurement scenario. Now, when you go to measurement scenario, we need to talk about metrology. In metrology, the idea is to measure some phase or the variation of the phase. And typically in optics, we do that with interferometry. So you convert phase into intensity, and then you measure intensity, and then you infer the phase value from the intensity measurement. So typically you have this sort of a plot that you obtain, and then you have a certain intensity value, and from that for that intensity, and there should be a unique phase value. So that's sort of the idea. Now, ideally, right, this plot that you observe in your detector should be aligned. But the problem is that lasers or all these light sources, they have so-called a quantum property, because photons, they mean light, it consists of photons. So there's a level of fluctuation. Because of the photon number distribution, the data actually looks like this. So it's just sort of, it has a spread. And this spread actually gives you uncertainty in terms of phase estimation. So if you apply information theory, you have a state preparation, and then you have a parameter, and then there's interaction, and eventually you have a measurement. And from the measurement, you have a certain measurement variance, or the standard deviation, which you can calculate from quantum mechanics. And then from this standard deviation, you can then infer the accuracy of your phase measurement. So delta phi and delta O, these are related. And at the best scenario, they can be equal. So there is a phase estimation uncertainty limit that you can really, you cannot go beyond this limit. So this is something that you can mathematically derive. Now, in quantum metrology, right, the idea is that you want to go from a standard, so-called standard quantum limit, and then go to Heisenberg limit. And this is going to be the ultimate limit that the quantum mechanics will give you. And it is sort of a commonly accepted that you need quantum resources to be able to go beyond this limit. But as you can see, these are highly impractical in many situations. Now, if you analyze this a little bit, and you don't really need entanglement to be able to do that. So just to give you an idea how you get to this phase estimation uncertainty relation, and you typically start with heuristically, energy and time uncertainty relation, and then you convert that into photon numbers, and then phase, and some simpler relation. And then you have end up with this delta phi, which is a phase uncertainty, and then delta n, which is a number uncertainty. So if there's a photon number fluctuation, this is going to be directly translated into phase uncertainty. And obviously, delta n is your particle property, right? So it's so interference is a wave property, and then delta n is a particle property. So somehow, let's say you have a laser. And laser is sort of we accept that the photon number distribution is Poissonian. So delta n, or the photon number statistics that you can infer delta n, or the standard deviation, is square root of the average photon number. It's well accepted, and you can easily calculate that. And it turns out delta phi is 1 over square root of n. And this is what's known as a standard quantum limit. And it turns out if you use a very exotic quantum state, you can go beyond that. And one example to do that is, if you want to go beyond, let's say, what standard quantum limit is going to give you, you need to make delta n larger, or as large as possible, given the total number of photons. And it turns out, if you can prepare a photon state that looks like this, so all the photons are in the upper path, or all the photons are in the lower path, and then if you can somehow make them in superposition, and that's what's known as a number path entangled state. And then it turns out delta n is, in this case, maximally n. So you can actually get to Heisenberg limit So that's kind of why entanglement comes in quantum metrology. But if you look at this a little bit carefully, you don't actually need entanglement to be able to achieve this, because it turns out, if you look at these equations a little bit carefully, right, this n times phase sensitivity actually comes from the fact that photons, they interact with the parameter phi n times before being detected. And accurate analysis will actually show that this is indeed the case. Entanglement turns out to be a convenient way to achieve this, but what's really needed is n-fold interaction before detection. So if you analyze a lot of quantum applications a little bit carefully, sometimes you start with entanglement, but then you can sort of go around it a little bit. And you don't really need entanglement. That's sort of a very, very fragile resource. So the idea here is that, well, you don't really need entanglement in many cases. Then is it possible to emulate this effect classically? And then can you utilize this classical effect or classical correlation for something useful? And it turns out there are a number of examples that you can actually achieve this. So in quantum optics, obviously you need quantum correlated photons or entangled photons. Typically, parametric down conversion in a crystal typically will give you that. Or classically correlated photons are actually quite easy to obtain, because light from the sun is already classically correlated. If you just split it by the beam splitter, two beams are classically correlated. So classically correlated beams are quite easy to obtain, although if you want to utilize it, you need to increase the intensity a little bit, and that becomes a technical problem. So just to give you an idea of this sort of analogy between the two, I'm going to give you, just pass on this one, just to give you the conclusion. You have what's known as a correlation interferometry. Your light source can be entangled photons, or your light source can be classically correlated photons. And then you have this correlation interferometer. And then the output, if you calculate, they are very similar but different. So when you have an entangled photons, the joint measurement actually gives you the one in the upper equation here. So the modulation is maximally, let's say, the visibility or is maximal. And then the interference actually relies on the coherence provided by the laser here. But if you have a classical correlation, light from the, let's say, sun, it turns out the correlations are still there, but the visibility is less. But the upside here is that it is insensitive to any coherence must be inherent in the system. So it's a completely incoherent, but nevertheless, it's going to exhibit very interesting second order and even third order coherence if you do it properly. So we have actually demonstrated this a few years ago. It's completely coherence insensitive interference phenomena. And the interpretation is can be done quite simply, but it requires a bit of quantum optics knowledge. So I will just pass through this. And what I want to convey here is that there are classical advantages. We always talk about quantum advantages, but there are classical advantages. But although we borrow some ideas from quantum mechanical systems, but in some cases, there are classical advantages. For instance, in this case, classical light will give you higher photon flux, and classical correlation is coherence insensitive, which is actually quite beneficial, unlike quantum coherence, because quantum coherence is really requires coherence. So when there is a decoherence, everything is just gone. And then classical correlation interferometry with non-coherent light, it's going to be quite robust to turbulence in the atmosphere, and you can actually apply this to actual ranging scenarios. So now, if you want to exploit these kind of classical advantages for sensing and remote ranging, it turns out there's a possible methodology that you can do that. So just to give you an idea, LiDAR is a very commonly accepted technology nowadays, right? Because you send the light and then you determine the time of flight for the reflected photon, and then you calculate how far the object is. But this kind of time-of-flight-based LiDAR, you can easily jam it because the other guy can simply send the pulse light and everything was just completely gone. Another LiDAR scheme is known as a coherent LiDAR. So basically, you send a laser beam and then you modulate the frequency and then you detect reflected beam and then you observe interference. And interference between the original frequency and then slightly different frequency will actually give you a beating. And from this beating, you can actually calculate how far the object is. Now, the coherent LiDAR is actually quite robust to jamming, but typically coherent LiDAR actually works in a rather close range because everything has to be coherent. So if the object is farther than the coherent length of the laser beam, it doesn't work. But our scheme is coherent and sensitive. So it's really, you can actually apply this to any distance. So we actually try to demonstrate this idea in a laboratory without going into details. So what we observe here is you have some object that's a little bit far away, and then we have a thermal source of light, and then we measure correlations between two detectors. Let's see, in this case, CMOS1 and CMOS2, and CMOS2 detects reflected light, and CMOS1 detects local light, and then we measure the correlation between the two. And this spatial correlation actually gives you this sort of interferogram, two-dimensional interferogram. And it turns out if you calculate the angle, and this angle directly translates into the object distance. And obviously, because of this sort of a thick interference fringe, calculating or the measuring angle directly is not that trivial because it translates into, obviously, distance and sensitivity or error. And what you can then do is to apply angle estimation algorithm. Quite simply, you do a Fourier transform and then you do apply Radon transformation. And it will allow you to calculate the angle very, very accurately. And with that angle, you can actually calculate how far the object is, regardless of your coherence of the beam that you're using. So just skipping this slide to the last one. So what I'm trying to say, I guess, is you have quantum interference related to entanglement. And then sometimes, because of decoherence, entanglement is gone, but still classical correlation is still left. Or you can build this classical correlation from purely classical sources. And then it turns out, when you apply this classical correlation to measurement scenario, the fundamental quantum limit obviously is not changed, right? Because it's physics. You cannot change the laws of physics that easily. But the thing is, you have certain gains here because it's coherence insensitive, so it can be quite pragmatic and more practical. It doesn't get affected by atmospheric turbulence, so you can actually apply it to real situations. And it's obviously immune to entanglement degradation due to decoherence. And the bare fact that you have a huge photon flux will allow you to improve practical signal-to-noise ratio, unlike quantum scenarios where you have the Heisenberg limit scaling, but the actual number of photons or number of particles are not that high. But in this case, n is already very, very high. So SNR is already quite high. So with that, I think you can try to find other examples or other unique applications where you have a classical correlation. And in this example, I only showed you a case where you have a two-particle correlations, but you can actually envision a scenario you have a multi-particle classical correlation, and then maybe you can use this to a measurement scenario, or probably communication is out of the option, but at least in the measurement scenario, this can be a useful approach in the near term until something can be really done when building large entangled state and being able to keep it for a long time. With that, I thank you for your attention.
Thank you, Professor Kim. So our final speaker is Professor Ki-hwan Kim, who will present the entanglement and spin squeezing with the 2D crystals of iron. Please give him a big round of applause.
Thank you for very kind introductions, also invitation to this very nice forum and symposiums. And also, I really feel thanks to all the audience that until this last minute stay here. So I hope I'm not much bored about it. So my name is Ki-hwan Kim, and most of so how can I use this laser pointers here. That's why all the other speakers didn't show about it. So let me see what I can do. Anyway, so in these times, now that more than 20 years, all I did is only about this trapped ions. So I just want to say, in my perspective, I want to share my perspective about trapped ions, especially nowadays, quantum information science or quantum computations and so on are getting more popular, including South Korea. And in these times in the quantum, thank you. Oh, thank you.
This works, no? Oh, it didn't work. Oh, what happened?
It's a kind of differential.
Differential.
That's differential.
Oh, so
that screen too bright.
Too
bright
I
for
see.
usual
That's
one.
why. Yeah, thank you. Yeah, thank you. You're right. Yeah. So only all I did about the trapped ions. So just basically at the end of this talks, if you remember ion trap or trapped ion is very. I might say I want to say it's the best the candidate for quantum computer or whatever quantum resource. But at least you feel like it's very interesting system. Also, it's good to explore more and more with this kind of atoms and ions. So if we have such a feeling, I feel very happy about after the end of this forum. Symposiums. So maybe with many other speakers, I briefly want to say about the three gentlemen that showing this quantum quantum mechanics is indeed really true. These people propose how to show when people are arguing about which is correct and so on. So they really almost no loophole, no other way. So it's a solid foundation they made. And then it is also Europeans, also many other people think with this quantum, and then we can do the communication and the computations and also some sensings and so on. So these are people exploring, and then even nowadays some people. This is from the McKenzie, where is it? Anyway, they estimate, it can be how good market eventually would be, and then they think about computing, also communication and sensing and so on. So even now there's no real revenue, no real market in some sense, but people keep expecting and so on. And then among them, just what I want to say is I'm mostly focusing on this trapped ions, although neutral atoms and Professor Keck and Yunho talk a lot about photonics, and Professor Chai was talking about superconducting systems and so on. There are many other candidates. And just want to say about this trapped ions and how this study is studied and developed. So the idea of a trapped ion, basically the dreaming of this Wolfgang Paul or Hans Demmert, these people think about how can we deal with individual atoms one by one. So a lot of nowadays solid state technology is very mature, and semiconductor device all made very nice device, cell phones and so on. But anyway, the very old times, around the 1940, they imagine, can we deal with individual atoms one by one? What can we do about it? And original what they thought is if we have some charge particle, so the charge, then if somehow make the discharge particle force to the middle, then maybe we can grab one atom or maybe a few atoms and can do some things about it. So that's their starting point, and unfortunately that's not possible. So by physics principles and so on, even though I fakely make the electric potential toward the center, but there is a hidden leaking area. So the electric field always leak to somewhere else. We cannot do about it. And then, the physics people always think something is impossible. Then maybe what will be the other way to get over it and so on. So, Wolfgang Paul developed this using oscillating electric field. So whenever this charge particle escape, by changing the direction, it may come back. So if you're changing this direction fast enough, then eventually you can grab some individual atoms or molecules and so on. So that's their starting point. And so because of their contribution, I think they started around the 1940s, something like this. And then these two people, one is using oscillating electric field, the other is using magnetic field. They realize really grabbing atoms in their systems. Actually, I was told it took more than 20 years from the original idea to realization. So it takes almost times, and they dedicated their life for these technologies. And that was the starting point. So nothing much we can do. Only all the charge particle people was able to grab, the particles, charge particles, and then David, not this way. David Wineland was the postdoc, or I think postdocs working with Hans Demelt, and then once they grab the atoms, so what they can do, they think a lot about it, and with the invention of laser, so he developed the method of using laser to control the atomic states. So this also takes more than 20 years. He did the first laser cooling around 1980, and then dedicated more than 20 years of his life, developed many technology to deal with individual quantum states of atoms, atomic ions. And because of his contribution, he won the Nobel Prize, and then the main idea is measuring and manipulating individual quantum states. So all he could do is now grab some atom, and then one, maybe two, some very small level, we can manipulate and detect. And later on, this quantum computer is nothing related to ion traps at that time. So people pushing what they wanted with individual atoms, and people, especially Peter Joller, maybe will soon come here for the Physics Society meeting. They think about this ion trap. Maybe it's a very good candidate for realizing quantum computer. So using these traps, anyway, using this side traps, and then with a lot of lasers. My technology of dealing with lasers. So all these things, independently developed, they found is very good to use for the quantum computer. And then this is the examples of our traps. We are inherited a lot of these technologies, and then this here is a vacuum chamber. Vacuum system. Here we take out every atoms. Here a lot of atoms and molecules take it out away, and then the oscillating electric field we generated in this device, and then we put the we also trap the individual atoms, and this is negative, positive charged individual atoms. People believe atoms very difficult to see with our eyes, but in this particular way, we can see the atom by atoms like this, and with the quantum computation idea, so this individual atom we use as a qubit. That's our starting point. And then these atoms is a charged particle, so they're actually repelling each other. They don't like to be at one place. They just, in some sense, hate each other. They just push away and so on. But somehow they have collective motions. So sometimes they are moving together, and then sometimes they are just the half go one way, the other way, and so on. They have this kind of collective motion, and then through this kind of collective motion, we may be able to do some quantum computation or some quantum operations and so on. So these are main ideas about using trapped ions, the system. So we have an individual atom that has well-defined two energy level. We are using, and then on top of that, it has some collective motions. And using these two parts, we can do something useful and so on. So and then this one of the advantage of this using trapped ions. In general, a lot of materials, including everywhere here, all atoms are very close to each other. So here you hear a lot about this coherence time. Basically, you want to have some quantum property as long as possible, especially it's capable of two different states existing at the same times. And then, so that's called the superposition. And in general, it's very difficult to maintaining this superposition. This is one of the key technology we need to know, the isolating all the noise perturbance and so on. And it's this atomic ion case. You can imagine these atoms levitated in the space, and then we take away every atoms. Basically, it's nothing. So this has itself a very good possibility of good coherence time. Theoretically, we are expecting of millions of years of coherence time we may have, and then we showed some technical way, just about 1.5 hour level. So, and it's more than my presentation. The coherence time can exist. So, and eventually, we will see this is more than days and so on. Right now, our students also working very hard. So we are approaching to over 3 hours, something like this. And using these atoms, strong point is all of this coherence property can be further enhanced and so on. And then this is not, so this superposition property with the atoms, and this is not the limitation at all. And later, we found the main limitation is not the atom, but the microwave source, classical source is the limitation for the moment. And this is one of the advantages, and then we are happy to of it showing this atoms property. And then this technical part, let me skip. And with this good coherence property, with the trapped ions, all what we do is basically using the laser beam, so many qubits, and then dealing with laser beam one by one, using manipulating quantum state. And if you want to make the two atoms entangled or related, we are using the two different lasers to do something about it. So these are the general idea. And then what people found is whenever you deal with only two, this case is there are many atoms, but not the many, but when we deal with only two, it works beautifully. If we tried about 10,000 times, maybe around 1 or 2 times failure, that's the world record nowadays. It works really well.
But whenever put more like this many, and the performance of this operation getting worse and worse. So how can we deal with such a problem? Is this Dave Wineland, the Nobel laureate, and what they imagine is maybe we can overcome this by engineering. So the idea is you may make the many this is all electrode because it's a charged particle. We can by controlling electric field you can move these ions going back and forth and so on. So whenever you do with the laser operation using very small number of ions, and then the most of the time maybe stay there away. So by moving the ions going back and forth, you can imagine this is basically engineering challenge, and you can scale up whatever you like. And just the problem is they imagine this one maybe early 2000, and then this is from the NIST groups. They push their works really long time, more than 20 years and so on, and then still is limited about the 4 qubit. So this 4 qubit experiment is done about early 2020. That was this NIST group's largest numbers. And then when I dealing with this trapped ion business, I thought this is not a good approach to pursue. So I was aware of this engineering developments and so on, but later on, around 2020, it's called, the company name is Continuum. They are making amazing progress. The NIST groups makes up to the 4 qubit level for 20 years, but this company is now they made this linear chain with up to 6 qubit, and then they enhanced this one to now 56 qubit level, and then they shows called the quantum supremacy data. If you look at this superconducting demonstration, so this part is means success rate. You can think. So you show some very complicated algorithm. How many times it succeed is all the superconducting level. The best one still, best one still around the 10 to minus 3 level. Means you run the 1,000 times, maybe one. You may have a perfect quantum correlations, but so this very, very small, but this ion system, they made a huge progress. Now about you do the 10 times, then roughly 3 times is really genuine in quantum rhythm operated. So this is one of amazing the experience for me. I thought that's the hopeless technology, but somehow people made amazing breakthroughs. And then another approach is this, you have many ions, and then we know this performing very bad because the people know the reason is this collective mode is as the number of ion increase is getting closer and closer, and then it's very difficult to deal with one by one. So when you have many ions, just let them do in fully quantum A. It's very complicated. But anyway, by checking out how they did and so on, you may have some way to deal with this the ions operation. And this approach is a lot pushed by IonQ. I heard nowadays most of Koreans know the name of this company. And also the IDQ is now related to this IonQ. So they are pushing these technologies as much as possible. And nowadays, these companies are doing very well. And as researchers, we have a really big pressures. What can we do more and so on. And then one of our thinking is dealing with not the linear chains of ions. So this is in one traps, another Innsbruck group says about the many ions, nicely dealing with all the operations and so on. We are considering, instead of linear chain, maybe making 2D crystals of ions. And in company, it looks like they are very mission oriented. They are pushing whatever they originally planned, and they didn't have a chance to look around other possibility. So for us, maybe for now it's a very good opportunity looking at different dimensions. So instead of one dimension, if we go to the two dimension, maybe we can do something more beyond the 1D. So obviously, compared to the 1D, 2D, if we just even add two more lines, immediately 3 times more qubit we can deal with. And then the many other technical aspects we are looking for could be better. So why the really big companies, this is obviously looks like compared to 1D, 2D crystal should be better. But why people didn't do much this direction? Because there are many problems, especially these ions trapped with oscillating electric field. Only when we are in the middle, there's no oscillating electric field. So if this ions a little bit away from this perfect line, and all ions are shaking a lot about it. So the people don't want to use such a kind of dirty situation. So the people didn't push much about it. But we developed some kind of traps, and then at least we saw the huge numbers of the ion. Actually, it still is about 270 level, so we need to go further and so on. But compared to 1D, 50 already very demanding, but we could do further. And for that, we were originally tried to make some kind of traps. We didn't think about 2D crystals, but some nice performing traps we tried to develop. And then we realized this is maybe very good for 2D crystals because when I briefly mentioned this oscillating electric field away from the center, it's called the micro motion. Anyway, it's some technical terms. It's all moving vertical. So if our lasers are perpendicular to this oscillating field, then basically these ions never feel any these lasers. Still very clean operation we are able to do. So that's what we found. And then this is now, but that started actually the 2013, something like this. One PhD student dedicated whole his PhD and barely make the performing traps. Many trials and errors and so on. And this is the latest version of our system. This one works about 10 ion, and then many ions stably holding very well. And then with that, when we had some bad performance trap, just given our limited situation, we could do something. So the one of called is related to quantum simulation, and then want to find some complicated interacting situation. What is the ground state? That was we tried, and then indeed in our experiment, the final states is more or less working as we expected. It's not perfectly working well because at that time the trap was not performing very well. But at least we can see main signature that complicated interaction situation was there compromising the stable state we found. And but now we have a much better performing traps, and then we thought about what can we do about it is anyway this 2D crystal business now maybe inspiring many other people. So nowadays also I feel worldwide competition from many other groups. And someone using much larger ions and so on. But so far, this stable 2D crystal, can we have entanglement or not? It was not fully demonstrated. And the panning trap case, people shows very fast oscillating trap they show some kind of spin squeezing entanglement. So here, roughly saying this size of this one is from the quantum mechanical uncertainty. And then as long as if you reduce this size, then you have some benefit. That's what Kim also mentioned about quantum advantage. And so we thought about we can do something similar as a starting point. So maybe I just don't want to say too much technical details, but with our stable 2D crystals of ion, we observe basically this no squeezing entanglement case. Some region we can see, and then as a little bit of entanglement, but sorry, actually this is I made a little bit mistakes, but we could see about minus 4 dB levels of spin squeezing entanglement. Roughly, when we have 10 ion, it works like 20 ions levels and so on. So this is we are quite excited about this spin squeezing entanglement with the 2D crystals, and then so far we did up to 27 ions. So this is for now the largest number that we can push, and then I don't know we can really go further or not, but at least as a starting of entanglement, we can. I don't think we can achieve this one near future, but about a month ago we started with about 10 ion. Now we are having some result of up to 27. And we want to push this one as much as possible. As this could be as a good basis to fully functioning computations or the operations, and maybe also quantum sensing can be used and so on. And with that, thanks for your attention.
Thank you, Professor Kim. So we'll now hear our closing remarks from Misao Sasaki, the director of APC-TP. Please give him a big round of applause.
Well, it's a bit early, but anyway, I first have to thank all the speakers, presenters, to give us very, very interesting and informative talks, and we have learned a lot. I hope all this information I gathered, well, I sort of tried to go through all the things, but I don't think I can do that because of lack of my knowledge and the ability and so on and so forth. Anyway, but I'd like to go through those slides maybe later to understand a little bit better about what's going on. But apparently in the world, huge sort of developments have been made, and well, it's very amusing, it's not just amazing, it's amusing to know all this progress. So, and I'm pretty sure that this progress is continuing and probably accelerating, just like the case of those, I forgot the name of this curve, the exponential curve for the speed of supercomputer, but now is everything in quantum science seems to go really rapidly into new stages, and according to some of the speakers, the terminology is the second what do you call revolutions, quantum revolutions, and or maybe this is in some sense, maybe we are entering a new paradigm. Anyway, and we do hope the APC-TP will contribute to this progress as well, and I hope you will also help, contribute. Anyway, thank you very much. Oh, sorry. And maybe finally, I should thank all those staff and the fact, people who helped to organize this workshop. So could you please just give applause to all these people who helped us, including the APCP staff. Thank you very much.
Thank you again for the remarkable ending speech. And so far, this concludes the in commemoration of the APEC 2025 APCTP Forum and Symposium on Prospective Quantum Technology. Once again, we would like to show our gratitude with your presence here today. And following the formal program, we'd like to invite all of you to join our barbecue dinner outdoor located at the cafe in the Student Union building today. So please follow our staff over there for the dinner venue. And again, thank you all for your presence here today and hope to see you again for the next year as well. Thank you. Please follow our staff over here for the dinner. This way, please. So following the formal program, we would like to invite you to join our barbecue dinner outdoor located at the cafe in the Student Union building. Please follow our staff over here for the dinner. This way, please.